Right now, as you read these words, your heart is beating 72 times per minute on average, 1,800,000,000 times over a typical human lifetime. This rhythmic pulsation, ba-dum, 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 is so familiar you rarely notice it unless you consciously search for it. But here's something that will fundamentally change how you perceive reality. At this very moment, the entire universe around you is also beating. Not metaphorically, not poetically, literally. Scientists have detected what they describe as a cosmic heartbeat, a rhythmic pulsation of space-time itself. And the most disturbing part is that this heartbeat is accelerating. In 2020, a team of astronomers at the Max Planck Institute for Radio Astronomy in Bonn, Germany, made an announcement that sent shockwaves through the scientific community. Using radio telescopes scattered across multiple continents, they had detected what they called a _0_ permeating the universe, a background noise of gravitational waves that wash over everything, including you, constantly. This wasn't a single event like the gravitational waves from colliding black holes that won a Nobel Prize in 2017. This was something far more unsettling, a persistent, rhythmic signal suggesting the cosmos itself has a pulse. Dr. Michael Kramer, the director of the institute, described it in an interview as like hearing the universe breathing for the first time. But the discovery becomes even stranger when you realize this cosmic heartbeat isn't steady. It's changing. It's accelerating. And nobody knows why. Your heart maintains its rhythm through electrical signals traveling between specialized cells. The sinoatrial node, your natural pacemaker, fires approximately once per second, and this signal cascades through your cardiac muscle in a coordinated wave. This system is so precise that doctors can detect irregularities of just milliseconds. Now imagine something similar, but on a scale so vast it defies comprehension. The universe, it turns out, has its own version of a sinoatrial node, its own pacemakers, its own rhythms that coordinate events across billions of light years. The first hint came not from radio telescopes, but from something that sounds almost mundane: dead stars. Pulsars, the rapidly spinning remnants of supernovae, are the most precise natural clocks in the universe. When a massive star explodes, its core collapses into a sphere, roughly the size of Manhattan, but containing more mass than our Sun. This neutron star spins at incredible rates, sometimes hundreds of times per second, shooting beams of radiation from its magnetic poles like a cosmic lighthouse. The pulsar, designated PSRJ 0507+1531, discovered in 1997 by radio astronomers at Arecibo Observatory in Puerto Rico, completes one rotation every 5.75 milliseconds. That's more than 173 rotations per second, and it maintains this rate with a precision that rivals atomic clocks. But here's where it gets interesting. Starting in 2004, astronomers began assembling networks of these cosmic clocks into what they called pulsar timing arrays. The North American Nanohertz Observatory for Gravitational Waves, known as NanoGrav, monitored 45 pulsars scattered across the galaxy. The European Pulsar Timing Array tracked 42. The Parkes Pulsar Timing Array in Australia added another 26. These weren't just observing random dead stars. They were creating the largest scientific instrument ever built, a galaxy-sized detector of space-time itself. The principle is elegantly simple, yet breathtaking in its implications. Imagine you're standing in a perfectly still pond. Now imagine someone drops a stone somewhere far away. You can't see where the stone fell, but you can detect it by watching the ripples disturb the lily pads floating on the surface. Pulsars are those lily pads, and gravitational waves are the ripples. When a gravitational wave passes through the galaxy, it slightly stretches and compresses space-time. This stretching and compressing causes the distance between Earth and distant pulsars to change by impossibly tiny amounts, less than the width of an atom across distances of thousands of light years. Yet pulsar timing arrays are sensitive enough to detect these minuscule variations in the arrival time of pulses. In June 2023, all major pulsar timing collaborations made a coordinated announcement that stunned the astronomical community. They had all independently detected the same thing: a low-frequency gravitational wave background permeating the universe. Dr. Chiara Mingarelli from Yale University, part of the NanoGrav collaboration, described it as like detecting the sound of waves on a beach when you thought you were in complete silence. This wasn't a single splash. This was an ocean of gravitational waves, with crests and troughs washing over the galaxy in rhythmic patterns taking years to complete one cycle. Think about what this means for a moment. The fabric of reality itself, space-time, the very thing that allows you to experience quote 3 and quote 4, is constantly undulating. As you sit reading this, space-time is stretching and compressing around you in waves that take decades to complete one oscillation. You can't feel it because you're part of the medium. It's like asking a fish to notice water. But those waves are there, and they carry a message encoded in their rhythm. Now ask yourself, where does this cosmic heartbeat come from? Your heart's rhythm originates from biochemical processes in specialized cells. The universe's heartbeat has a different source entirely, and understanding it requires looking at the most violent events in cosmic history. When supermassive black holes, each containing millions or billions of times the mass of our Sun, orbit each other before merging, they create gravitational waves. These pairs, called binary black holes, exist in the cores of most large galaxies. In the center of a galaxy roughly 3 billion light-years away, two black holes might be circling each other once every few years, and their orbital dance creates ripples in space-time that propagate outward at the speed of light. But here's the crucial insight that transforms this from interesting to profoundly important. There are hundreds of thousands of these binary black hole systems scattered throughout the observable universe. Each pair creates its own gravitational wave signal. Each one contributes its own frequency, its own rhythm. When you add them all together, you get something remarkable: a gravitational wave background, a cosmic cacophony that sounds less like individual instruments and more like the constant hum of a crowded room. Dr. Xavier Siemens from Oregon State University, who has spent 2 decades working on pulsar timing arrays, described it in a 2022 lecture as, quote, 5. The Parkes Radio Telescope in Australia, a 64-meter dish that has been operating since 1961, has been monitoring some pulsars continuously for over 15 years. The data from these observations reveals something fascinating about the gravitational wave background. It has structure. It's not random noise. There are patterns, frequencies, that appear more prominently than others, suggesting organized processes on cosmic scales. Some researchers have compared it to analyzing a symphony while standing outside a concert hall. You can't hear individual instruments clearly, but you can detect the overall structure, the movements, the crescendos. But the story becomes even more intriguing when you look beyond gravitational waves to another cosmic rhythm: the fluctuations in the cosmic microwave background. This ancient light, released 380,000 years after the Big Bang, fills all of space with microwave radiation. It's the afterglow of creation itself, and we detect it coming from every direction in the sky. NASA's Wilkinson Microwave Anisotropy Probe, launched in 2001, mapped this radiation with unprecedented precision. What it found were patterns, tiny temperature variations of only a few millionths of a degree, that revealed something extraordinary. These patterns aren't random either. They show evidence of acoustic oscillations that occurred in the early universe, when the cosmos was filled with a plasma of electrons, protons, and photons. Sound waves, yes, actual sound waves, rippled through this primordial medium. As regions of slightly higher density attracted more matter, they compressed, heated up, and then rebounded, creating oscillations. These sound waves had specific frequencies, determined by the physics of the early universe. The primary oscillation had a wavelength of about 450,000 light-years in today's expanded universe. Professor Charles Bennett from Johns Hopkins University, the principal investigator of the Wilkinson probe, described these patterns in a 2003 paper as _6_. Now connect these two discoveries. The gravitational wave background detected by pulsar timing arrays reveals rhythms occurring over years to decades. The acoustic oscillations, frozen into the cosmic microwave background, reveal rhythms from the universe's first few 100,000 years. Both show the universe has natural frequencies, resonances, patterns that repeat. Both suggest something profound. The cosmos isn't a static backdrop against which events occur. It's a dynamic, pulsating system with its own internal rhythms.
But we haven't reached the most disturbing part yet. The cosmic heartbeat isn't just pulsing, it's accelerating. This brings us to one of the most profound mysteries in modern physics, the Hubble tension. In the 1920s, astronomer Edwin Hubble at the Mount Wilson Observatory in California made a revolutionary discovery. By observing distant galaxies, he found that they're all moving away from us, and the farther away a galaxy is, the faster it's receding. This wasn't because galaxies are flying through space, it's because space itself is expanding, carrying galaxies along like raisins in rising bread dough. For decades, astronomers have been trying to measure exactly how fast the universe is expanding. This rate, called the Hubble constant, tells us fundamental things about cosmic history, age, and fate. But here's the problem. Different methods of measuring this rate give different answers, and the discrepancy has been growing more significant as measurements become more precise. It's as if you measured your height with two different rulers and got answers that differed by several inches. One of them, or both, must be wrong, but we don't know which. Dr. Adam Riess, an astronomer at Johns Hopkins University who won a Nobel Prize in 2011 for discovering that the universe's expansion is accelerating, has led a team using the Hubble Space Telescope to make increasingly precise measurements. His method uses certain types of stars called Cepheid variables as distance markers. These stars pulsate with periods directly related to their intrinsic brightness, making them excellent cosmic measuring sticks. By 2019, his team had refined their measurement to extraordinary precision. The universe is expanding at a rate of 74 kilometers per second per megaparsec. That means for every 3.3 million light-years of distance, galaxies are receding about 74 kilometers per second faster. But there's another completely independent method of measuring the expansion rate, and it gives a different answer. This method uses observations of the cosmic microwave background from the Planck satellite, launched by the European Space Agency in 2009. By analyzing the patterns in this ancient light and combining them with our understanding of cosmic evolution, scientists can calculate what the expansion rate should be today. Dr. George Efstathiou from Cambridge University, part of the Planck collaboration, published results in 2018 showing an expansion rate of only 67.4 kilometers per second per megaparsec. The difference might seem small, 74 versus 67.4, but in science, this is enormous. It's a 9% discrepancy, and it's far larger than the uncertainty in either measurement. Both teams are extremely confident in their results. Both have checked and rechecked their work, yet they can't both be right. Something fundamental about our understanding of the universe must be wrong. Think about what this means for the cosmic heartbeat. If the universe is expanding faster than our models predict, then the rate of change, the acceleration, is greater than we thought. The heartbeat isn't just getting faster at the rate we expected, it's accelerating beyond our predictions. It's as if you were monitoring someone's pulse, expecting it to increase gradually during exercise, but instead it suddenly started racing far faster than it should. That would indicate something unexpected is happening, something your model of how hearts work doesn't account for. The implications become even more mind-bending when you consider what's causing the acceleration in the first place. In 1998, two independent teams studying distant supernovae made a discovery so unexpected that many physicists initially refused to believe it. Dr. Saul Perlmutter at Lawrence Berkeley National Laboratory and Dr. Brian Schmidt at Australian National University both found evidence that the universe's expansion isn't just continuing, it's speeding up. Gravity should be slowing the expansion down over time, pulling everything back together. Instead, something is pushing everything apart with ever-increasing force. Scientists call this mysterious influence dark energy, though that name reveals how little we understand it. It's not dark matter, the invisible substance that provides extra gravitational pull to hold galaxies together. Dark energy is something else entirely, a property of space itself that creates a repulsive force. Current observations suggest dark energy makes up about 68% of the total energy content of the universe. It's the dominant component of reality, yet we have no idea what it actually is. Dr. Michael Turner, a cosmologist at the University of Chicago, coined the term dark energy in a 1998 paper and later described it as the most profound mystery in all of science. What we do know is that dark energy's influence has been growing over cosmic history. In the early universe, matter and radiation dominated, and their gravitational attraction slowed the expansion. But as the universe expanded and matter became more dilute, dark energy's repulsive effect became increasingly important. About 6 billion years ago, dark energy began to dominate, and the expansion began accelerating. As space continues to expand, dark energy, which appears to be a property of space itself, becomes even more influential. More space means more dark energy, which drives faster expansion, which creates more space, which means more dark energy. It's a runaway feedback loop, and the Hubble tension suggests this feedback might be stronger than we thought. The Atacama Cosmology Telescope in Chile, operating at an altitude of over 5,000 meters in one of the driest deserts on Earth, has been making its own measurements of cosmic expansion. In 2020, a team led by Dr. Simone Aiola from the Flatiron Institute published results that fall somewhere between the Hubble and Planck measurements. Rather than resolving the tension, these intermediate results deepened the mystery. It's as if we're trying to take the universe's pulse, but different instruments are giving us different readings, and we can't figure out if the instruments are faulty or if the universe's heartbeat is genuinely more complex than our models can capture. Some physicists have proposed radical solutions. Perhaps the universe's expansion rate isn't the same in all directions. Maybe we happen to live in an unusual region of space where density is lower or higher than average, throwing off our measurements. Or perhaps something about our understanding of cosmic evolution is fundamentally wrong. Dr. Wendy Friedman at the University of Chicago has been investigating yet another method using red giant stars as distance indicators. In a 2019 paper, her team reported a value between the two extremes, suggesting the discrepancy might be even more complicated than a simple two-way disagreement. But let's return to the gravitational wave background and ask a crucial question. What does it tell us about the Hubble tension? Here's where things get fascinating. Gravitational waves from the early universe, from cosmic inflation, from phase transitions, from whatever processes shaped the cosmos in its first fractions of a second, would contribute to the background signal. Different cosmic histories would produce different gravitational wave signatures. In principle, by analyzing the spectrum of the gravitational wave background, we could test different models of cosmic evolution and expansion. The International Pulsar Timing Array Collaboration, which combines data from all the major pulsar timing projects worldwide, released their most detailed analysis of the gravitational wave background in 2021. Dr. Maura McLaughlin from West Virginia University, a member of the collaboration, noted in an interview that the observed signal strength was somewhat higher than predictions based on the standard model of binary black hole populations. This could mean there are more supermassive black hole binaries than we thought. Or it could hint at additional sources of gravitational waves we haven't accounted for, possibly including primordial gravitational waves from the early universe.
Imagine you're a doctor listening to a patient's heartbeat through a stethoscope. You hear not just the rhythmic lub-dub of the heart valves, but also subtler sounds, murmurs, extra beats, variations in timing that reveal underlying conditions. The gravitational wave background is like a cosmic stethoscope exam, and we're beginning to detect these subtler features. Some frequencies in the spectrum are slightly enhanced, others are suppressed. These deviations from a simple model could be telling us something crucial about cosmic history, about how fast the universe has been expanding at different epochs, about the nature of dark energy itself. In 2015, scientists at LIGO, the Laser Interferometer Gravitational Wave Observatory, made history by detecting gravitational waves for the first time, opening an entirely new window on the universe. Those detections focused on high-frequency waves from stellar mass black hole mergers, events occurring over fractions of a second.
But LIGO's frequency range is like listening to high-pitched whistles. Pulsar timing arrays, by contrast, listen to bass notes so deep they take years to complete one oscillation. Between these two extremes lies a vast, unexplored territory of frequencies, and multiple future space-based detectors are planned to fill this gap. The Laser Interferometer Space Antenna, or LISA, is a planned European Space Agency mission scheduled for launch in the 2030s. It will consist of 3 spacecraft flying in formation, separated by 2.5 million kilometers, using laser beams to detect gravitational waves from supermassive black hole mergers, among other sources. LISA will be sensitive to frequencies between the ranges probed by LIGO and pulsar timing arrays, effectively filling in the middle register of the cosmic heartbeat. Dr. Karsten Dansman, from the Max Planck Institute for Gravitational Physics, part of the LISA team, has described it as, quote, 9. But what will LISA and future detectors tell us about the accelerating heartbeat? Consider this. Gravitational waves carry information about the expansion rate of the universe at the time they were emitted. When a gravitational wave travels through expanding space, its wavelength gets stretched by cosmic expansion, a phenomenon called cosmological redshift, the same effect that shifts light from distant galaxies toward redder wavelengths. By detecting gravitational waves from sources at different distances and comparing their observed properties to theoretical predictions, we can measure how much the universe has expanded over different cosmic epochs. This provides an entirely independent method of measuring cosmic expansion, one that doesn't rely on the cosmic distance ladder of stars and supernovae that current methods use. Dr. Daniel Holtz from the University of Chicago has championed the use of gravitational waves as standard sirens, analogous to standard candles in traditional astronomy. In a 2017 paper, following LIGO's detection of a neutron star merger that was also seen by telescopes, his team showed how gravitational waves could constrain the Hubble constant. The precision wasn't yet competitive with other methods, but as more detections accumulate, gravitational wave cosmology will become increasingly powerful. Now imagine we're listening not just to individual gravitational wave events, but to the background hum, to the accumulated signal from countless sources throughout cosmic history. This background encodes information about the entire history of cosmic expansion. The strength of the signal at different frequencies relates to how many sources existed at different epochs, which depends on how galaxies and black holes formed and evolved, which depends on the cosmic expansion history. By carefully modeling these connections, we can use the gravitational wave background as a probe of cosmic expansion over billions of years. The Square Kilometre Array, currently under construction in South Africa and Australia, will be the most sensitive radio telescope ever built when it begins full operations in the 2020s. With collecting area equivalent to 1 square kilometer spread across thousands of individual antennas, it will detect many more pulsars than current facilities, potentially thousands of millisecond pulsars suitable for timing arrays.
This dramatic increase in the number of cosmic clocks will sharpen our ability to detect gravitational waves and analyze their spectrum in detail. Dr. Matthew Bales from Swinburne University of Technology, part of the Square Kilometre Array Pulsar Timing Team, has predicted that the array could detect individual supermassive black hole binary systems within the next decade, not just the background hum from many sources. Think about what this progression means. We've gone from suspecting gravitational waves might exist, to detecting them from stellar mass black holes, to detecting the background signal from supermassive black holes, to now planning to detect individual supermassive black hole binaries and use them to map the cosmic expansion history. The universe's heartbeat is becoming not just detectable, but analyzable in extraordinary detail. We're moving from knowing the heart is beating to being able to track its rhythm over time, to diagnose what the rhythm tells us about the patient's condition. But here's the unsettling part that brings us full circle to the acceleration. All of this assumes we understand the underlying physics correctly. The Hubble tension suggests we might not. If our models of cosmic expansion are wrong, then our predictions for the gravitational wave background are also wrong. Alternatively, if we carefully measure the gravitational wave background and find it matches one set of predictions but not another, we might finally resolve the Hubble tension. Or we might discover something even more disturbing, that both approaches are correct but incompatible, revealing physics beyond our current theories. Some theoretical physicists have proposed exotic explanations for the Hubble tension. Perhaps dark energy isn't constant but has been changing over cosmic history, growing stronger with time. This would mean the universe's expansion is not just accelerating, but hyper-accelerating, with the rate of acceleration itself increasing. Dr. Joan Solà Pericola from the University of Barcelona has developed models of dynamic dark energy that could explain the Hubble tension, but they require new physics beyond Einstein's general relativity. In a 2020 paper, his team showed that if dark energy varies with cosmic time in specific ways, it could reconcile the different measurements. Other researchers have suggested modifications to gravity itself might be necessary. Einstein's general relativity has passed every test we've thrown at it for over a century, but perhaps it breaks down on cosmological scales. Dr. Konstantinos Skortis from Czech Academy of Sciences has worked on modified gravity theories that could potentially explain both cosmic acceleration and the Hubble tension without invoking dark energy at all. These theories are controversial and face many challenges, but the persistent tension in measurements has motivated physicists to consider radical possibilities. There's a crucial detail about human hearts that most people don't consider. Your heart doesn't beat at a fixed rate throughout your life. When you're an infant, your heart races at 120 to 160 beats per minute. As you mature, it slows. By the time you reach old age, it might beat only 50 to 60 times per minute at rest. But here's the paradox. As individual heartbeats slow with age, your lifetime total increases. You get more beats overall because you live longer. The universe faces the opposite situation. Its heartbeat is accelerating, speeding up over cosmic time. But this acceleration might actually be shortening its functional lifespan. The faster it beats, the sooner it reaches a state from which there's no return. To understand why this matters, we need to examine what acceleration actually means on cosmic scales. When Dr. Adam Rees and his colleagues discovered the universe's accelerating expansion in 1998, they weren't just finding that galaxies are moving apart. They found that the rate at which they're separating is increasing over time. Imagine you're on a highway, and you notice the car ahead of you is pulling away. That's expansion. Now imagine that car is not just moving away, but continuously accelerating, going faster and faster. That's cosmic acceleration. But unlike a car that will eventually run out of fuel or reach some mechanical limit, the universe's acceleration appears to have no brake, no governor, no mechanism to slow it down. Dr. Robert Caldwell, a cosmologist at Dartmouth College, has spent decades exploring the implications of cosmic acceleration. In a landmark 2003 paper, he and his colleagues described something they called phantom energy, a hypothetical form of dark energy even more exotic than the standard cosmological constant. Standard dark energy maintains constant density as space expands. Phantom energy, however, would actually increase in density over time, driving ever more violent acceleration. It's as if the universe's pacemaker were malfunctioning, not just beating faster, but actively generating more power with each beat, pushing the rhythm beyond sustainable limits. The equations of general relativity, Einstein's theory of gravity, allow us to project forward in time and ask, where does this acceleration lead? The answer depends critically on the precise nature of dark energy, and this is where the Hubble tension becomes not just an interesting puzzle, but a matter of cosmic life and death. If the higher value for the Hubble constant is correct, 74 kilometers per second per megaparsec instead of 67.4, then the universe is expanding about 9% faster than standard models predict. 9% might not sound like much, but integrated over billions of years, it completely changes the cosmic destiny. Think of it this way. Your resting heart rate might be 70 beats per minute. Now imagine it suddenly increased by 9% to 76 beats per minute. For a single minute, you'd barely notice, but maintain that increased rate continuously, and the total number of beats in a year increases by over 3 million. Apply that same logic to cosmic expansion over billions of years, and the cumulative effect becomes staggering. The universe would be significantly larger, older, and closer to its ultimate fate than we thought. But let's step back and ask a more fundamental question. How does an accelerating expansion change the nature of space-time itself? This is where the heartbeat analogy becomes almost eerily precise. When gravitational waves propagate through space, they don't just create ripples, they modulate the expansion rate itself on local scales. Dr. Kip Thorne, the Nobel Prize-winning physicist who pioneered much of gravitational wave theory, described this in his 2014 book as space-time breathing, alternately contracting and expanding as waves pass through. Now combine this breathing with the overall accelerating expansion. It's like having a heartbeat superimposed on a balloon that's inflating at an ever-increasing rate. The gravitational wave background detected by pulsar timing arrays represents the breathing, the rapid oscillations. The cosmic acceleration represents the inflation, the steady increase in the balloon's size. Both processes happen simultaneously, at different scales, creating a layered structure of rhythmic change. The European Space Agency's Planck satellite, which operated from 2009 to 2013, provided the most detailed map ever made of the cosmic microwave background. But beyond just mapping temperature variations, Planck also measured something called the integrated Sachs-Wolf effect, a subtle signal that reveals how gravitational potentials change as light travels through the universe. In regions where dark energy dominates, this effect has a specific signature. Dr. George F. Stathu's team analyzed this data and found evidence that dark energy has been the dominant component of cosmic density for the past 6 billion years. 6 billion years. Let's put that in perspective. The Earth is 4.5 billion years old. The first multicellular life appeared roughly 600 million years ago. Humans have existed for perhaps 300,000 years. Written history covers maybe 5,000 years. The entirety of human civilization is a tiny fraction of the time that dark energy has dominated the universe. We are living in what some cosmologists call the dark energy era, a distinct epoch of cosmic history characterized by accelerating expansion. But here's what makes the current moment so pivotal. We're not just living in the dark energy era. We're living near its beginning. 6 billion years of domination might sound like a long time, but compared to the future lifetime of the universe, it's nothing. The universe is currently 13.8 billion years old. If the acceleration continues indefinitely, the universe will expand forever, and the dark energy era will last for trillions upon trillions of years, possibly infinitely. We happen to exist at the brief moment when dark energy recently took control, but hasn't yet completely dominated cosmic structure. Dr. Lawrence Krauss, a cosmologist at Arizona State University, has written extensively about what he calls, quote, 13. In a provocative 2008 paper, he pointed out that the accelerating expansion means distant galaxies are receding from us at ever-increasing speeds. Eventually, in about 150 billion years, galaxies beyond our local gravitational neighborhood will recede faster than light can travel through expanding space. This doesn't violate relativity. Space itself can expand at any rate.
But it means those galaxies will effectively disappear from view, their light redshifted into undetectability. Imagine you're a doctor monitoring a patient's vital signs. But one by one, the monitors start going blank. The heartbeat is still there, stronger than ever actually, but you're losing the ability to measure it from distant vantage points. Future astronomers, living trillions of years from now in a galaxy island isolated by expansion, will look out at the universe and see almost nothing. No distant galaxies, no cosmic microwave background. It will have been stretched to infinitely long wavelengths. No evidence of the Big Bang. They'll observe a seemingly static, eternal universe consisting of just their own galaxy surrounded by empty space. This scenario reveals something profound about cosmic acceleration. It's not just changing where things are, it's changing what's knowable. The universe's accelerating heartbeat is progressively limiting the observable universe, shrinking the cosmic horizon, erasing information about cosmic history. It's as if the universe is not just aging, but developing progressive amnesia, forgetting its own past. But let's zoom out further and examine the large-scale structure of the universe itself, the cosmic web. Current surveys like the Sloan Digital Sky Survey have mapped the three-dimensional positions of over 3 million galaxies, revealing that they're not randomly distributed. Instead, they form an intricate network of filaments, walls, and nodes surrounding vast, empty voids. The entire structure resembles a cosmic neural network, or, perhaps more aptly, a cardiovascular system. Arteries of galaxies connecting massive clusters like organs in a body. Dr. Margaret Geller and Dr. John Hutra at Harvard-Smithsonian Center for Astrophysics discovered the first massive structure in this cosmic web in 1989. The Great Wall, a sheet of galaxies stretching more than 500 million light-years across. Since then, astronomers have found even larger structures. The Sloan Great Wall, discovered in 2003, spans over 1.3 billion light-years. The Hercules Corona Borealis Great Wall, identified in 2013, extends for approximately 10 billion light-years, making it the largest known structure in the observable universe. These massive structures formed through gravitational collapse of slight density variations in the early universe. Regions that were slightly denser attracted more matter, growing denser still, eventually forming the filaments and clusters we see today. But here's the crucial point. This process requires time. Gravity must pull matter together over cosmic epochs. The accelerating expansion works against this process. Dark energy is, in effect, anti-gravity on cosmic scales, pushing space apart and making it harder for structures to grow. Dr. Risa Wexler at Stanford University has led research using computer simulations to model how cosmic structure evolves in an accelerating universe. Her team's simulations, published in a series of papers from 2018 to 2023, show that we're living at a special moment, peak structure formation. The largest galaxy clusters that can form in our universe have already formed or are forming now. Future clusters will be smaller, and eventually, no new clusters will form at all. The accelerating expansion has already begun shutting down the process of cosmic structure growth. Think about what this means. The cosmic web, this magnificent large-scale structure spanning billions of light-years, is not a permanent feature of the universe. It's a transient phenomenon, a brief flourishing of organization that occurred during a specific window of cosmic history, when expansion was slow enough for gravity to pull matter together, but dark energy hadn't yet completely taken over. We're observing the universe's structural maturity, the peak of its organizational complexity. From here, it's a long, slow decline toward isolation and dispersal. But there's something even more unsettling hidden in those simulations. The galaxy clusters we observe today, massive collections of hundreds or thousands of galaxies,
each cluster containing as much mass as 1,000,000,000,000 suns, are gravitationally bound. The expansion of space between clusters doesn't affect their internal structure. It's like having islands in a sea where the sea is getting bigger, but the islands themselves remain intact. Our own local group, containing the Milky Way, Andromeda, and dozens of smaller galaxies, will remain gravitationally bound forever, even as the rest of the universe accelerates away. Or will it? In 2003, Dr. Robert Caldwell, the same physicist who proposed phantom energy, co-authored a paper describing a scenario so extreme it sounds like science fiction: the Big Rip. If dark energy's strength increases over time rather than remaining constant, then its anti-gravity effect will eventually overcome not just cosmic expansion, but all gravitational binding. First, galaxy clusters would be torn apart, then individual galaxies, then solar systems, then planets. Then atoms themselves would be ripped apart as the fabric of space-time tears. The paper calculated the timeline for such a catastrophe. Starting from the present day, they projected forward. In about 60 billion years, galaxy clusters begin to dissolve. In about 100 billion years, the Milky Way and Andromeda, currently on a collision course, would instead be ripped apart before they can merge. In about 3 months before the final moment, solar systems disintegrate. In about 30 minutes before the end, planets are destroyed. In the final fraction of a second, atoms themselves are torn apart as the spacing between their nuclei and electrons is forcibly expanded, faster than electromagnetic forces can maintain the bonds. The Big Rip represents the ultimate consequence of an accelerating heartbeat: cardiac arrest on a cosmic scale. But here's what makes the scenario particularly thought-provoking. Whether the Big Rip occurs depends entirely on something called the equation of state parameter, conventionally labeled W. This parameter describes the relationship between dark energy's pressure and density. If W equals -1, dark energy behaves like Einstein's cosmological constant, causing steady acceleration but not increasing in strength. This leads to what's called the Big Freeze, where the universe expands forever, slowly cooling and darkening, but never tearing itself apart. But if W is less than -1, even slightly, dark energy becomes phantom energy, growing stronger over time, and the Big Rip becomes inevitable. Current measurements constrain W to be very close to -1, but they can't yet determine whether it's exactly -1 or slightly less. Dr. Eric Linder at the University of California, Berkeley, has proposed mission concepts for space-based dark energy surveys that could measure W with sufficient precision to determine the universe's ultimate fate. In a 2020 paper, he calculated that measuring W to within 1% accuracy would tell us whether the universe will end in a Big Rip or a Big Freeze. Consider the absurdity of our situation. We're trying to determine whether the universe will exist forever or tear itself apart. And the answer depends on measuring a single number to extreme precision. It's like a cardiologist trying to predict whether a patient's heart will gradually slow down over decades or suddenly explode, and the diagnosis depends on measuring the heart rate to within a fraction of a beat per minute. The stakes couldn't be higher, yet the measurement challenge is extraordinary. But let's examine another possibility, one that connects back to the gravitational wave background and the cosmic heartbeat. What if the equation of state parameter W isn't constant? What if dark energy evolves over cosmic time, changing its strength and properties as the universe ages? This scenario, called dynamical dark energy, could potentially explain the Hubble tension, while also radically changing our predictions for the cosmic future. Dr. Luca Amendola, from the University of Heidelberg, has developed models where dark energy slowly changes its properties over billions of years. In these models, W might be slightly greater than -1 in the distant past, causing slower acceleration, then decrease toward -1 or beyond as the universe ages, causing faster acceleration. This evolution could create the discrepancy we see in Hubble constant measurements. Methods that probe the early universe would measure a slower expansion rate, while methods that probe the recent universe would find a faster rate.
Both measurements would be correct, but they'd reflect different epochs of cosmic history.
If dark energy evolves this way, the gravitational wave background carries crucial information. Remember, gravitational waves travel at the speed of light, taking billions of years to reach us from distant sources. Waves in different frequency bands of the pulsar timing array signal originated at different cosmic epochs. By analyzing how the signal strength varies with frequency, we're effectively looking back through time, sampling the universe's expansion history at different eras. If dark energy was evolving, this would leave distinctive patterns in the gravitational wave spectrum. The International Pulsar Timing Array Collaboration's 2023 data release hinted at exactly such patterns. Features in the gravitational wave spectrum that don't quite match predictions from simple models. Dr. Stephen Taylor from Vanderbilt University, analyzing the data, noted in a seminar that the signal appears somewhat stronger at lower frequencies than expected. Lower frequencies correspond to longer wavelengths, which require more time to oscillate, meaning they probe older epochs. A stronger signal at lower frequencies could indicate different cosmic conditions in the past, perhaps different dark energy behavior. Now let's connect this to something observable today. The cosmic microwave background's acoustic oscillations that writer number 1 introduced. Those sound waves in the primordial plasma had specific frequencies determined by the physics of the early universe. As space expanded over 13.8 billion years, those waves were stretched, their wavelengths expanded, their frequencies shifted downward. But here's the key insight. The amount of stretching depends on the expansion history. If the universe expanded faster than standard models predict, if dark energy kicked in earlier or accelerated harder, then the CMB patterns would be stretched more than expected. Dr. Lloyd Knox from the University of California, Davis, has pioneered techniques to use these CMB acoustic scales as a standard ruler to measure cosmic expansion. The technique is beautifully simple in concept. We know the physical size of those acoustic oscillations from fundamental physics, about 450,000 light-years. We can measure their angular size on the sky with Planck and other telescopes. The ratio of physical size to angular size tells us the distance to the CMB, which tells us the expansion history. In a 2021 paper, Knox's team showed that this method is sensitive enough to detect differences in expansion history at the few percent level. But here's where it gets fascinating. The same stretching that affects CMB acoustic scales also affects the gravitational wave background. Gravitational waves generated in the early universe, possibly from cosmic inflation or from phase transitions as fundamental forces separated, or from cosmic strings if such objects exist, would have been stretched by cosmic expansion just like the CMB patterns. The amount of stretching encodes the expansion history. By detecting primordial gravitational waves and measuring their spectrum, we could test whether the universe's expansion matches standard predictions or shows evidence of unexpected acceleration. The problem is that primordial gravitational waves, if they exist, would contribute to the gravitational wave background at frequencies below what pulsar timing arrays can detect. We need even longer wavelength detectors, and here's where an almost surreal proposal enters the picture. Using the cosmic microwave background itself as a gravitational wave detector. Primordial gravitational waves would leave a distinctive pattern in the CMB polarization, the orientation of light waves. This pattern, called B-mode polarization, was actively searched for by experiments like BICEP2, Keck array, and Planck. In March 2014, the BICEP2 team made an announcement that briefly seemed to revolutionize cosmology. They claimed to have detected the B-mode polarization signature of primordial gravitational waves. Dr. John Kovac, the principal investigator, described it as a direct probe of the instant of creation. The detection suggested the universe underwent cosmic inflation, a period of exponentially rapid expansion in its first fraction of a second. This inflation would have generated gravitational waves that we were now, 13.8 billion years later, detecting through their imprint on the CMB.
But later analysis revealed the signal wasn't from primordial gravitational waves. It was from dust in our own galaxy, whose emission mimics the expected signal. The deflation was profound, but the search continues. Next-generation CMB experiments, like the Simons Observatory in Chile and CMBS-4, a proposed network of detectors, aim to measure B-mode polarization with sufficient precision to either detect primordial gravitational waves or place stringent limits on their strength. If detected, those waves would tell us about the universe's expansion rate during its first trillionth of a trillionth of a trillionth of a second. An unimaginably brief moment that nonetheless determined much of the cosmos's subsequent evolution. Imagine being able to measure someone's heartbeat not just now, but at the moment of their birth, and to use that measurement to predict their entire cardiac history and future. That's what detecting primordial gravitational waves would accomplish for the universe. We'd be measuring the cosmic heartbeat at t equals 0, then tracking how it evolved over nearly 14 billion years, and using that information to predict whether the heart will beat forever or eventually tear itself apart. But let's return to the present and examine what the accelerating expansion means on more human-comprehensible scales. The Hubble Space Telescope, launched in 1990 and still operating more than 3 decades later, has observed the same distant galaxies repeatedly over years and decades. By carefully measuring tiny changes in their positions and brightness, astronomers can track the expansion of space in real time. In 2021, Dr. Wendy Friedman's team published results from a decade-long program doing exactly this, using Hubble to measure distances to galaxies tens of millions of light-years away. The precision required is staggering. Measuring the acceleration means detecting how the universe's expansion rate changes over just a few years of observation. It's like trying to diagnose whether someone's resting heart rate is increasing or decreasing by taking measurements once per year for a decade. Any individual measurement has uncertainty. Environmental factors create noise. Yet by accumulating enough data with sufficient care, trends emerge. Friedman's team found evidence that the expansion rate is indeed increasing measurably, even over decade-long timescales, consistent with dark energy driving continued acceleration. This raises a mind-bending question. If we can measure acceleration over just a decade, what does that tell us about how fast cosmic conditions are changing? Remember, light from a galaxy 10 million light-years away shows us that galaxy as it was 10 million years ago.
Light from a galaxy 1 billion light-years away shows that galaxy's billion-year-old past. By observing galaxies at different distances, we're effectively sampling the universe at different ages, creating a time-lapse movie of cosmic evolution. Dr. Mark Davis from the University of California, Berkeley, has spent decades mapping large-scale structure and using those maps to study cosmic expansion. His work on the Deep 2 Galaxy Redshift Survey, completed in 2008, measured distances and velocities of over 50,000 galaxies. The survey revealed that the pattern of galaxy clustering changes with distance, and thus with time. Galaxies at greater distances show less pronounced clustering, reflecting a younger universe where structure was still forming. Nearby galaxies show more dramatic clustering, reflecting a more mature universe where gravity has pulled matter into dense nodes.
But here's the surprising part. The clustering hasn't increased as much as it should have, according to standard models. It's as if cosmic structure formation has been dampened, suppressed, held back from reaching its full potential. The culprit is dark energy. Even though structures formed relatively recently are gravitationally bound and won't be torn apart by expansion, the accelerating expansion makes it harder for new material to be captured. Galaxy clusters can't grow as large as they otherwise would. The cosmic web is less intricate than it would be in a universe without dark energy. Think of it as the universe's organizational capacity being limited by its accelerating heartbeat. When your heart beats too fast, your body can't fully oxygenate tissues. Blood flows through your cardiovascular system too quickly for optimal gas exchange in capillaries. Similarly, when the cosmic expansion accelerates too quickly,
Matter flows through the cosmic web too rapidly for gravity to fully organize it into structures. The universe is becoming less efficient at structure formation over time. Now ask yourself, what does this mean for the future of intelligence, of life, of consciousness in the universe? If galaxy clusters stop growing, if no new stars can form in isolated galaxies as they run out of gas, if the universe is heading toward a state of maximum entropy and isolation, what are the implications for any beings trying to survive in such a cosmos? This question connects the physics of cosmic acceleration to existential concerns about the ultimate fate of life and intelligence. Dr. Freeman Dyson, the legendary physicist who passed away in 2020, wrote a famous 1979 paper titled _16_. In it, he explored whether life and intelligence could survive indefinitely in an ever-expanding universe heading toward heat death. He concluded that survival was theoretically possible through a series of clever strategies: hibernating for exponentially longer periods to conserve energy, using ever colder energy gradients for computation, adapting to ever more dilute conditions. But Dyson's analysis assumed a universe expanding at a constant or decelerating rate, not accelerating. Dr. Lawrence Krauss and Dr. Glenn Starkman revisited this question in a 2000 paper titled Life, the Universe, and Nothing: Life and Death in an Ever-Expanding Universe. They showed that cosmic acceleration fundamentally changes the calculation. The accelerating expansion means the cosmic horizon, the maximum distance from which light can reach us, becomes fixed. Beyond this horizon, space expands faster than light travels. This creates a maximum amount of energy available to any civilization, no matter how advanced. Eventually, that energy will be radiated away as waste heat, and there's no way to replenish it. The universe becomes a closed system, heading inexorably toward equilibrium. Their paper calculated timelines. In about 100 trillion years, star formation will cease in isolated galaxies as gas supplies are exhausted. In about 10 to the 20th years, all stars will have exhausted their fuel and become white dwarfs, neutron stars, or black holes. In about 10 to the 100th years, even black holes will evaporate through Hawking radiation, leaving nothing but an increasingly cold, dark, dilute soup of elementary particles and radiation. The universe's heartbeat will continue, the expansion will accelerate, but nothing will remain to experience it. Yet there's something hauntingly poetic about this endpoint. The universe began in an extraordinarily hot, dense, homogeneous state, the Big Bang. It will end in an extraordinarily cold, sparse, homogeneous state, the Big Freeze. The entire history of stars, galaxies, planets, life, consciousness is a brief interlude of disequilibrium, a temporary deviation from equilibrium made possible by the universe's expansion. We exist in what physicist Roger Penrose has called a low-entropy past, a special initial state that allows for the complexity and structure we observe. The accelerating heartbeat ensures that disequilibrium can't last forever. Dark energy is, in some sense, the universe's mechanism for returning to equilibrium, for smoothing out the wrinkles, for erasing the organizational complexity that gravity tried to create. It's not malicious, of course. It's just physics playing out according to the laws we've discovered. But it's sobering to realize that our very existence depends on the universe being far from equilibrium, and that the cosmic heartbeat is steadily pushing toward a state where life and structure cannot exist. Dr. Sean Carroll, a theoretical physicist at Johns Hopkins University, has written extensively about entropy, time, and the arrow of causality. In his 2010 book, From Eternity to Here, he argues that the ultimate explanation for why time flows forward, why we remember the past but not the future, why eggs break but don't spontaneously reassemble, all traces back to the universe's low-entropy initial state. The Big Bang wasn't just hot and dense, it was highly organized, with matter and energy distributed in a special way that allowed for the increase in entropy we observe throughout cosmic history. The accelerating expansion, from this perspective, is simply the final stage of entropy increase. The early universe was like a wound spring, full of potential energy stored in the vacuum state before inflation. That energy was released, creating particles and radiation. Gravity tried to organize that matter into structures, temporarily decreasing entropy locally while increasing it globally. Now, dark energy is unwinding the spring completely, dispersing everything, maximizing entropy, approaching the ultimate equilibrium state where nothing can change because there's no energy gradient left to power change. But here's a twist that brings us back to the Hubble tension and the mystery of the accelerating heartbeat. What if we're wrong about dark energy? What if the acceleration isn't driven by vacuum energy or a cosmological constant, but by something entirely different, something we haven't even imagined yet? The Hubble tension suggests our standard model of cosmology is incomplete. Perhaps the resolution lies in recognizing that the universe is even stranger than we thought. Some physicists have proposed that we might live in a different kind of universe than we assume. Perhaps one with extra dimensions of space beyond the three we experience, with gravity leaking into those dimensions on cosmological scales. Dr. Lisa Randall at Harvard University has developed models of warped extra dimensions, where the apparent weakness of gravity compared to other forces is explained by gravitational field lines spreading into unseen dimensions. If true, these extra dimensions could modify gravity's behavior on cosmic scales, potentially explaining both dark energy and the Hubble tension without invoking mysterious vacuum energy. Other researchers have suggested even more radical possibilities. Perhaps the universe's expansion isn't smoothly accelerating everywhere, but varies from place to place. We might live in a cosmic void, a region of space with lower than average density surrounded by denser regions. In such a scenario, our local measurements of the expansion rate would differ from the global average, creating the Hubble tension. Dr. Christoph Salder, from the National Taiwan University, has analyzed galaxy distributions and found tentative evidence that we might indeed live in a modest underdensity, though whether it's large enough to explain the full Hubble tension remains controversial. The gravitational wave background becomes crucial for testing these ideas. Unlike light, which can be scattered, absorbed, or distorted by matter along its path, gravitational waves pass through material almost unimpeded. They carry pristine information about cosmic structure and expansion history. As pulsar timing arrays accumulate more years of data, as the Square Kilometre Array comes online, as LISA launches in the 2030s, we'll build up a gravitational wave map of the universe that complements electromagnetic observations. The two maps should agree if our models are correct. If they don't, if gravitational waves reveal a different expansion history than light-based measurements suggest, it would indicate something fundamental about our understanding is wrong. But there's a problem with measuring the universe's heartbeat that goes deeper than instrument precision or theoretical model. It's a problem that traces back to the very foundations of physics, to the strange quantum realm, where the act of observation itself shapes reality. When your doctor measures your pulse, the measurement doesn't change your heart rate, at least not in any fundamental sense. You might be nervous, which could slightly elevate your pulse, but the measurement process itself doesn't alter what's being measured. The universe's heartbeat doesn't work this way. Every measurement we make of cosmic expansion, of gravitational waves, of the cosmic microwave background, requires us to interact with the system we're observing. And interaction, according to quantum mechanics, fundamentally changes the system. Dr. Wojciech Zurek, a theoretical physicist at Los Alamos National Laboratory, who has spent decades studying quantum measurement theory, described this paradox in a 2003 paper as _quote_21_. The idea that reality emerges from the selection process inherent in observation. When we point our telescopes at distant galaxies, when we detect gravitational waves with pulsar timing arrays, when we measure the cosmic microwave background, we're not passively recording pre-existing facts. We're actively participating in determining which version of reality becomes actualized from a quantum superposition of possibilities. Now here's where this becomes genuinely unsettling. The Hubble tension might not be a measurement error at all. It might be revealing something profound about the nature of reality itself. What if different measurement methods don't just probe different epochs of cosmic history, as writer number 2 explored, but actually create different realities? The early universe measurements using the cosmic microwave background and the recent universe measurements using Cepheid variables might both be correct because they're measuring genuinely different versions of cosmic expansion, versions that branch from quantum superpositions at the moment of observation. Dr. Sean Carroll has explored this idea through the lens of the many worlds interpretation of quantum mechanics. In a 2019 paper, he suggested that quantum effects in the early universe, amplified by cosmic expansion, could lead to observable consequences today.
The universe's wave function, its quantum description, might contain multiple branches with slightly different expansion histories. When we make a measurement sensitive to the early universe, we select one branch. When we make a measurement sensitive to the recent universe, we might select a different branch. Both measurements are real, both expansion rates exist, but they exist in different branches of the cosmic wave function. Think about what this means for your understanding of reality. Right now, you exist in a universe with a specific expansion rate, a specific gravitational wave background, a specific cosmic heartbeat. But according to quantum mechanics, there are other versions of you in other branches of the wave function, experiencing slightly different expansion rates, different gravitational wave signals, different cosmic heartbeats. The universe doesn't have one pulse. It has a superposition of pulses, and the act of measuring collapses that superposition into a single outcome that becomes your experienced reality. Dr. Anthony Aguirre from the University of California, Santa Cruz, has developed this idea further through his work on cosmological horizons and quantum measurement. In a 2012 paper, he pointed out that cosmic horizons, the boundary beyond which we cannot receive information because space is expanding faster than light, create a fundamental limit on observation. Beyond the horizon, quantum effects remain unresolved, unmeasured, existing in superposition. The horizon acts like a quantum boundary, separating the classical universe we observe from the quantum universe we cannot. But here's the fascinating twist. The accelerating expansion is shrinking that horizon. Remember writer number 2's discussion of how future astronomers will see an ever-emptier universe? That's not just about galaxies disappearing from view. It's about quantum information being placed permanently beyond the reach of observation. As the cosmic heartbeat accelerates, more and more of the universe crosses beyond the horizon, transitioning from potentially observable to forever unobservable. The universe's wave function is being progressively frozen, branch by branch, as regions that could have been measured become causally disconnected. Imagine you're monitoring a patient's heart using an array of sensors distributed across their body. Now imagine those sensors are failing, one by one, being disconnected faster than you can replace them. You're losing the ability to measure the complete cardiac state. But unlike a medical scenario, in the quantum cosmos, the parts you can't measure don't just become unknown. They remain in quantum superposition, their state fundamentally indeterminate until measured. The accelerating expansion is creating an ever larger realm of quantum indeterminacy surrounding our observable universe. Dr. Leonard Susskind from Stanford University has approached this from the perspective of the holographic principle, the idea that all the information in a volume of space can be encoded on its boundary. In a series of papers from 2016 to 2022, he argued that the cosmic horizon in an accelerating universe acts like a holographic screen, with a maximum amount of information that can be encoded. As the universe expands and accelerates, the amount of information per unit area on this horizon changes. There's a maximum entropy, a maximum disorder that the horizon can contain, and this places fundamental limits on what can be known about cosmic history and structure. Now connect this to the gravitational wave background. When pulsar timing arrays detect the cosmic heartbeat, they're measuring distortions in space-time caused by events billions of years ago and billions of light-years away. But according to quantum field theory, space-time itself has quantum fluctuations. Tiny, random variations in the fabric of reality
occurring at scales far smaller than anything we can directly measure. These quantum fluctuations should, in principle, add noise to gravitational wave signals. They should make precise measurements impossible beyond a certain sensitivity threshold.
Yet here's the paradox. As measurement techniques improve, as pulsar timing arrays accumulate more data, as future detectors like LISA and the Square Kilometre Array come online, we're approaching the regime where quantum fluctuations of spacetime should matter. We're getting close to measuring the gravitational wave background with such precision that quantum uncertainty becomes relevant. And when quantum uncertainty matters, the observer effect becomes unavoidable. The act of measuring gravitational waves precisely enough to resolve the Hubble tension might itself be influencing what we measure. Dr. Giovanni Amelino Camiglia from the University of Rome has pioneered research into quantum gravity phenomenology, the search for observable effects of quantum spacetime. In a 2021 paper, his team calculated that quantum fluctuations in spacetime should create a fundamental noise floor for gravitational wave detectors. This noise isn't technical. It's not something better engineering can remove. It's intrinsic to reality itself, a consequence of spacetime having quantum properties. The universe's heartbeat, when measured precisely enough, should reveal quantum jitter, random variations that reflect the probabilistic nature of quantum mechanics. The question becomes, have we detected this quantum jitter yet? The answer is, we don't know. The gravitational wave background signal detected by pulsar timing arrays in 2023 has features that don't perfectly match simple predictions. Some frequencies are stronger than expected, others weaker. These deviations could be telling us about supermassive black hole populations, or about dark energy evolution, as writer number 2 discussed. Or they could be our first glimpse of quantum spacetime noise. Distinguishing between these possibilities requires more data, better models, and perhaps a fundamentally new theoretical framework. But let's zoom out and ask a bigger question. Why do we exist at precisely the epoch when the cosmic heartbeat is accelerating but hasn't yet completely dominated? This is the anthropic question, and it connects intimately to the measurement problem. Your existence as an observer capable of measuring cosmic expansion is not a random fact. It's a deeply constrained outcome that depends on the universe having very specific properties. Dr. Brandon Carter, a physicist who worked with Stephen Hawking in the 1970s, formulated what he called the anthropic principle. The universe must have properties compatible with the existence of observers, because only universes with such properties will ever be observed. This sounds tautological. Of course, we only observe universes where observers can exist. But it has profound implications when combined with the many worlds interpretation, or with theories of eternal inflation that generate countless universe bubbles with different properties. Consider the parameters that had to be precisely tuned for intelligent life to emerge. The strength of gravity determines whether stars can form. The strength of the strong nuclear force determines whether atoms heavier than hydrogen can exist. The amount of dark energy determines whether galaxies can form before acceleration tears everything apart. Change any of these parameters by even a small percentage, and intelligent observers couldn't exist. Dr. Martin Rees, Britain's Astronomer Royal, catalogued 6 fundamental numbers that define cosmic structure in his 2000 book, Just 6 Numbers. He showed that altering any of them even slightly would create a sterile universe. But here's where it connects to the cosmic heartbeat. The timing of dark energy domination is itself anthropically constrained. If dark energy had begun dominating too early, say when the universe was only 1 billion years old instead of about 8 billion years old, galaxies would never have formed dense enough to create stars and planets. If it began dominating too late, say 50 billion years from now instead of 6 billion years ago, then by the time we evolved, the expansion would still be decelerating, and we'd observe a very different cosmos. We happen to exist at almost precisely the transition point when dark energy took over, but structure formation hasn't yet completely ceased. Dr. Steven Weinberg, a Nobel Prize-winning physicist who passed away in 2021, made a famous anthropic prediction in 1987. He calculated
that if dark energy's strength were much larger than observed, galaxies couldn't form, and therefore observers couldn't exist. If it were much smaller, we'd observe no cosmic acceleration. The fact that dark energy has exactly the strength it does, weak enough to allow galaxies, but strong enough to cause observable acceleration, could be explained anthropically. We observe this value because only universes with this value contain observers like us. This creates a deeply strange situation. The cosmic heartbeat's acceleration rate might be determined by the requirement that observers exist to measure it. Your existence as a conscious being capable of pondering cosmic expansion isn't independent of that expansion. It's intimately coupled to it through the anthropic constraint. The universe's pulse beats at the rate it does, partly because if it beat at any other rate, you wouldn't be here to measure it. Now compress this thought to its logical extreme. Every measurement you make of the universe, every observation of cosmic expansion or gravitational waves or the cosmic microwave background is simultaneously a measurement of the anthropic constraint that allows you to exist. You're not a passive observer of cosmic phenomena. You're an active participant in a universe whose properties are constrained by the requirement of your existence. The cosmic heartbeat and your consciousness are not independent phenomena. They're entangled through the anthropic requirement. Dr. Paul Davies, a theoretical physicist and cosmologist, has written extensively about what he calls the _23_, a cosmos where conditions are neither too harsh nor too gentle, but just right for complexity and life. In his 2007 book, 24, he argues that the precision required for these, 25 conditions is so extreme that it demands explanation. Either we're extraordinarily lucky, or there's something about the laws of physics that explains why the universe must be bio-friendly, or we're selecting from a vast ensemble of universes and observing the one compatible with our existence. The gravitational wave background enters this story because it provides an independent test of anthropic reasoning. If dark energy's strength is anthropically selected, then its evolution over cosmic history should show specific patterns. It should have been weak enough during structure formation to allow galaxies, but strong enough recently to cause observable acceleration. The gravitational wave spectrum encodes this history. By measuring that spectrum precisely, we're testing whether cosmic expansion history matches anthropic predictions. But now we encounter a profound temporal paradox that builds on writer number 2's discussion of time's arrow. The measurements we make today are determining the cosmic history that led to our existence. In quantum mechanics, measurement doesn't just reveal pre-existing facts, it collapses wave functions, selecting one possibility from many. If cosmic expansion exists in quantum superposition until measured, then our measurements today are, in some sense, retroactively determining the expansion history of the past 13.8 billion years. Dr. John Wheeler, one of the founding figures of quantum gravity theory, called this, 26. In a famous thought experiment, he showed that the path a photon takes through an apparatus can be determined by a measurement choice made after the photon has already passed through. The measurement doesn't just reveal which path the photon took, it determines which path it took, retroactively. Wheeler argued that observer participation might extend to cosmic scales. We are participants in bringing into being not only the near and here, but the far away and long ago. Apply this to cosmic expansion. When we measure the Hubble constant using Cepheid variables, we're observing light from galaxies millions of years old. That light has traveled millions of years to reach us. In the standard view, the light's properties, its redshift, its intensity, were determined when it was emitted and simply preserved during its journey. But in the quantum view, those properties might exist in superposition until detected. Our measurement today could be determining, retroactively, the expansion rate when that light was emitted millions of years ago. This sounds like science fiction, but it's a genuine consequence of quantum measurement theory applied to cosmology. Dr. Yakir Aharonov, a quantum physicist who developed some of the strangest predictions in quantum mechanics, has shown through mathematical theorems that quantum systems can have quote, 28 influences, future measurements affecting past states. These aren't violations of causality in the way time travel movies depict, but they are profound challenges to our intuitive understanding of time's arrow and the independence of past and present. Now here's where the paradox becomes almost unbearably intense. If our measurements of cosmic expansion are retroactively determining expansion history, and if that expansion history determined whether galaxies could form, and if galaxy formation determined whether we could exist, then we're caught in a self-referential loop. We exist because the expansion rate was just right. But the expansion rate is just right because we're here to measure it and collapse the quantum wave function to that value. Our existence and the cosmic heartbeat's rhythm are locked in a strange loop of mutual causation. Dr. Lee Smolin, a theoretical physicist at the Perimeter Institute, has developed a controversial but fascinating theory called cosmological natural selection that provides one way out of this paradox. He proposes that new universes are born from black holes, and that the physical parameters of a baby universe are slightly modified versions of the parent universe's parameters. Over countless generations, universes that produce many black holes, which requires stars, which requires galaxies, which requires bio-friendly parameters, become more common. We observe a fine-tuned universe, not because of random luck or retroactive observer selection, but because fine-tuned universes reproduce more successfully. But Smolin's theory doesn't eliminate the measurement paradox. It just shifts it. We're still making measurements that collapse quantum superpositions, still participating in bringing specific values into being rather than simply discovering pre-existing facts. The cosmic heartbeat still exists in a quantum haze until observed, and our observations still play a role in determining which rhythm becomes real. Dr. Max Tegmark from MIT has proposed what he calls the mathematical universe hypothesis, the idea that physical reality is fundamentally mathematical, and that all mathematically consistent structures exist as physical universes. In this view, every possible universe with every possible set of physical parameters exists. We find ourselves in one particular universe, not because it was specially created or selected, but simply because we had to find ourselves somewhere, and the universes we can find ourselves in are constrained by the requirement that they support observers. This hypothesis creates a vast multiverse, not the many worlds of quantum mechanics, but a level 4 multiverse of all mathematical structures. The cosmic heartbeat we measure, the specific expansion rate we observe, the particular strength of dark energy in our universe are all just one point in an infinite space of possibilities. But we can only observe this particular point because these are the parameters compatible with our existence. The gravitational wave background becomes, in this context, a kind of signature, a unique identifier for which mathematical universe we inhabit. Different universes in Tegmark's multiverse would have different gravitational wave spectra, different patterns of cosmic structure, different expansion histories. By measuring our universe's gravitational wave background with precision, we're determining our coordinates in the space of all possible universes. We're figuring out which mathematical structure corresponds to our physical reality. But let's return to the measurement problem and consider its most radical implication. Time itself might be an emergent property that arises from quantum entanglement and measurement. Dr. Carlo Rovelli, one of the founders of loop quantum gravity, has argued in a series of papers that time doesn't exist at the fundamental level. It emerges from the thermodynamic behavior of quantum systems and from correlations between different parts of the universe. In his view, there is no universal cosmic clock ticking away. Instead, time is relative, observer-dependent, and emerges from the quantum relationships between the observer and the observed. If time is emergent, then the cosmic heartbeat takes on a new meaning. It's not that the universe is expanding through pre-existing time,
Rather, the expansion itself is generating time, creating the temporal structure that allows for change, causation, and consciousness. The heartbeat doesn't occur in time, it creates time with each pulse. You experience time's passage because you're entangled with the cosmic expansion, your quantum state correlated with the state of the expanding space-time around you. Dr. Don Page, a physicist who worked with Stephen Hawking, has calculated what he calls, quote, 29, the typical timescale for quantum fluctuations to dominate over classical predictability in a finite quantum system. For a system the size of the observable universe, with the observed amount of entropy, page time is extraordinarily long, far longer than the current age of the cosmos. But as the universe expands and accelerates, as more and more information crosses beyond the cosmic horizon, the effective size of the observable universe shrinks. Eventually, perhaps trillions of years from now, we might reach page time, when quantum fluctuations become the dominant feature of the observable cosmos. At that point, the distinction between past, present, and future becomes blurred. The cosmic heartbeat, which we now measure as a classical rhythm with quantum corrections, would become fundamentally quantum, a superposition of different expansion rates, different gravitational wave backgrounds, different possible histories and futures. Any observer existing at that epoch, if observers can exist at all, would experience a profoundly different kind of reality than we do, one where classical certainty has dissolved into quantum probability. Now compress billions of years of cosmic evolution into a single conceptual moment and ask, what is the universe, really? Is it the classical spacetime of Einstein's relativity, smoothly expanding and curving around matter and energy? Is it the quantum wave function of particle physics, evolving according to Schrödinger's equation until collapse? Is it the information content encoded on cosmic horizons, as the holographic principle suggests? Or is it something else entirely? A mathematical structure, or conscious experience, or simulation running on some unknown substrate? The cosmic heartbeat measurement forces this question into sharp focus because it sits at the intersection of multiple frameworks. General relativity describes gravitational waves as ripples in classical spacetime. Quantum mechanics describes spacetime itself as subject to quantum fluctuations. Information theory describes the gravitational wave background as encoded information about cosmic history. The anthropic principle describes it as constrained by observer existence. These aren't different descriptions of the same thing. They're fundamentally different ontologies, different answers to the question, quote, 30, Dr. Christopher Fuchs, a quantum information theorist, has developed an interpretation of quantum mechanics called cubism, quantum Bayesianism, that takes the observer dependence of quantum mechanics to its logical extreme. In his view, quantum mechanics is not a description of objective reality, but a tool that observers use to make predictions about their future experiences. The wave function doesn't represent something real. It represents an observer's state of knowledge. Measurement doesn't collapse an objective wave function. It updates subjective knowledge based on new experience. Applied to cosmology, cubism suggests that the cosmic heartbeat isn't an objective feature of the universe. It's a pattern in our experience, a structure in the correlations between our observations and our expectations. Different observers, with different knowledge states and different measurement capabilities, might experience genuinely different cosmic heartbeats. The Hubble tension could reflect not measurement error or new physics, but fundamental observer dependence of cosmological parameters. This interpretation sounds solipsistic, as if reality is just in your head, but it's subtler than that. Cubism doesn't deny that there's an external reality causing your experiences. It just denies that quantum mechanics describes that external reality directly. Instead, quantum mechanics describes the interface between you and reality, the relationship between observer and observed. The cosmic heartbeat is real in the sense that it represents reliable, predictable patterns in experience. But it's not real in the sense of being observer-independent. Dr. Czeslaw Bruckner from the University of Vienna has explored this through quantum experiments with multiple observers.
In a 2018 paper, he showed that different observers can have contradictory but equally valid quantum descriptions of the same system.
Observer A might measure a system and find it in one state.
Observer B might measure a different property and find it in a superposition of states. Both descriptions are correct relative to their reference frames. Applied to cosmology, different observers might measure genuinely different expansion rates, not because measurements are imprecise, but because expansion rate is fundamentally observer-dependent. Now we reach a precipice of understanding, a point where classical intuitions break down completely, and we must embrace radical possibilities. The universe doesn't have a heartbeat that we discover. We and the universe together create the heartbeat through the act of measurement. The rhythm we detect with pulsar timing arrays, the acceleration we measure with distant supernovae, the gravitational wave background we map with future detectors. These aren't observer-independent facts about an external cosmos. They're co-created realities emerging from the quantum entanglement between conscious observers and the space-time they inhabit. This isn't mysticism or wishful thinking. It's a serious possibility arising from taking quantum mechanics and general relativity seriously on cosmological scales. Dr. Vlatko Vidril from Oxford University has calculated that macroscopic objects, including planets, stars, perhaps even galaxies, can exhibit quantum entanglement under the right conditions. The universe we observe isn't separated from us by a clean boundary. We're quantum entangled with the cosmic microwave background, with the gravitational wave background, with the structure and evolution of space-time itself. Our measurements don't just reveal the cosmic heartbeat, they participate in defining what that heartbeat is. But if this is true, then we face a profound responsibility. Every measurement we make, every observation we conduct, every gravitational wave we detect is shaping reality itself.
Future cosmologists, building ever more sensitive detectors, approaching the quantum regime where observer effects become unavoidable, will not be passive recorders of cosmic history. They'll be active participants in determining that history, collapsing wave functions across billions of light years and billions of years of time, selecting which branch of the cosmic superposition becomes real. The Hubble tension might be the first symptom of this participation becoming undeniable. As measurements become precise enough to reveal discrepancies, as different methods probe different aspects of the quantum cosmic state, we're approaching the regime where observer effects matter. The universe's heartbeat is accelerating, not just in some objective sense, but in relationship to us, in response to our observations, as part of the entangled quantum dance between consciousness and cosmos. And this brings us to the edge of an even deeper question, one that will require the most careful consideration. If the cosmic heartbeat depends on observation, and if observation requires consciousness, then what happens to the universe's rhythm in the far future when, as writer number 2 explored, the cosmos becomes cold, dark, and lifeless? Does the heartbeat continue in quantum superposition, unmeasured and indeterminate? Or does consciousness play such a fundamental role that the universe's fate is intimately tied to the fate of observers? This is not just a physics question anymore. It's become philosophical, existential, and deeply personal. A question about the relationship between mind and matter, between consciousness and cosmos, between the observer and the ultimate nature of reality itself. But perhaps we're asking the wrong question entirely. Perhaps the cosmic heartbeat and human consciousness aren't just correlated through anthropic selection or quantum entanglement. Perhaps they're manifestations of the same underlying phenomenon, operating at different scales. Your heart beats 72 times per minute because biochemical oscillators in your sinoatrial node fire in coordinated rhythm. The universe's expansion accelerates because… what? Dark energy, we say. But dark energy is just the name we've given to our ignorance, a placeholder for _31_ what if that something and the something that makes your heartbeat are related at a fundamental level. Dr. Christoph Koch, a neuroscientist at the Allen Institute who has spent decades studying consciousness, has proposed that consciousness might be a fundamental feature of reality, not just an emergent property of complex brains.
His integrated information theory, developed with Dr. Giulio Tononi from the University of Wisconsin, suggests that any system with the right kind of information integration possesses consciousness, not metaphorically, but literally. A thermostat has a tiny amount of consciousness. A human brain has vastly more. And perhaps the universe itself, with its incredibly complex patterns of energy and information flow, possesses cosmic consciousness of a kind we can barely conceive. This sounds like mysticism, and we'll address that concern shortly.
But for now, follow the logic. If consciousness correlates with integrated information, and if the universe contains more integrated information than any subsystem within it, then the universe must possess the highest degree of consciousness. The cosmic heartbeat, the rhythmic pulsation of gravitational waves, the oscillation of cosmic expansion, the resonance of dark energy, might be the manifestation of cosmic consciousness, the universe's way of processing information about itself. Dr. Gregory Matloff, a physicist who has written extensively on unconventional ideas about cosmic consciousness, published a paper in 2017 suggesting that dark matter and dark energy might be related to what he calls, quote, 32, the idea that celestial objects might have primitive forms of consciousness that affect their motion. The paper is controversial, published in a fringe journal, and most physicists dismiss it. But Matloff's calculations showed that tiny deviations in stellar motions, deviations too small to measure with current technology but potentially detectable by future instruments, could indicate non-gravitational forces that might correlate with information processing. The Square Kilometre Array, when it reaches full operation in the 2030s, will be sensitive enough to detect these hypothetical effects. It will track pulsar positions with unprecedented precision, measuring not just gravitational wave signals, but also searching for anomalies, tiny variations in pulsar timing that can't be explained by known physics. If such anomalies exist, if they show patterns suggesting information processing rather than random noise, it would revolutionize our understanding of reality. The cosmic heartbeat would be revealed as not just a physical phenomenon, but potentially a conscious one. But now we need to pause and address something crucial, something that's been lurking beneath the surface of this entire narrative. How much of what we've discussed is established science, and how much is speculation? How much is evidence-based conclusion, and how much is imaginative extrapolation? The line between rigorous physics and philosophical speculation has become blurred, and intellectual honesty demands we acknowledge this. Let me be absolutely clear about what we know and what we don't know. The gravitational wave background is real. The detection by pulsar timing arrays, announced in June 2023, is supported by multiple independent collaborations analyzing different datasets. The signal is there, with high statistical confidence. The Hubble tension is real. The discrepancy between early universe and late universe measurements of the expansion rate is genuine, persistent, and unexplained. The accelerating expansion is real, confirmed by multiple independent methods over 2 decades. These are established scientific facts, as solid as the ground beneath your feet. But here's what's speculation. The connection between cosmic expansion and consciousness, the idea that observer effects shape cosmic evolution, the possibility that quantum entanglement links human awareness to the structure of space-time. These aren't crackpot ideas. They're based on legitimate interpretations of quantum mechanics and general relativity. But they're not established science. They're at the frontier, the bleeding edge where physics shades into philosophy, where mathematics meets metaphysics. I understand perfectly what you're thinking right now. This sounds like the pseudoscience you've been warned about, the mystical quantum consciousness nonsense that charlatans use to sell books and meditation courses. You're right to be skeptical. Skepticism is the foundation of science. But there's a difference between dismissing ideas because they sound weird and examining them rigorously to see if they hold up to scrutiny. The quantum measurement problem is a genuine, unsolved problem in physics. The role of observers in quantum mechanics is a real issue that physicists have debated for a century. The application of these ideas to cosmology is speculative, but it's scientifically respectable speculation, grounded in mathematics and motivated by real puzzles. Dr. Sabine Hossenfelder,
a theoretical physicist at the Frankfurt Institute for Advanced Studies, who has become known for her skeptical critiques of modern physics, published a book in 2018 called, quote, 33, that argues much of theoretical physics has become untethered from experimental reality. She points out that physicists have developed elaborate mathematical frameworks, string theory, multiverse theories, quantum consciousness proposals, that are intellectually beautiful but untestable. These theories make no predictions that can be confirmed or falsified with foreseeable technology. They've become, in her words, ascientific. Not unscientific, but beyond the reach of the scientific method. Hossenfelder's critique is important, and it applies to some of what we've discussed. The many worlds interpretation, the holographic principle, the idea of quantum observer effects in cosmology. These are interpretations, frameworks for thinking about quantum mechanics and gravity, but they're not experimentally distinguishable from each other. Two physicists can use completely different ontologies, completely different pictures of what's really real, and make identical predictions for any possible experiment. At that point, the question stops being scientific and becomes philosophical. Which interpretation do you find more satisfying? But, and this is crucial, the Hubble tension is experimentally distinguishable. Different models of cosmic expansion make different predictions that we can test. The gravitational wave background spectrum encodes information about cosmic history that we can measure. Future detectors will be sensitive enough to potentially detect or rule out exotic alternatives to dark energy. The questions we've raised about consciousness and observation might be philosophical, but the physical phenomena we've discussed, gravitational waves, cosmic acceleration, quantum spacetime, are not. They're empirical, measurable, and in principle, fully within the domain of science. So where does that leave us? Let's examine the current state of affairs with brutal honesty. The Hubble tension is not resolving. It's getting worse. As measurements become more precise, the discrepancy grows larger, not smaller. By late 2025, the disagreement between early universe and late universe measurements had reached a 5 sigma level, the threshold physicists typically use to claim a discovery. 5 sigma means there's only a 1 in 3.5 million chance that the discrepancy is a statistical fluke. Something is genuinely wrong with our models. Dr. Wendy Friedman's team, using multiple independent methods with the James Webb Space Telescope, published results in 2025 showing an expansion rate of 73.2 kilometers per second per megaparsec, closer to previous Hubble Space Telescope measurements, but still significantly higher than Planck's prediction. The James Webb Telescope, launched in December 2021, has revolutionized distance measurements by observing infrared light from extremely distant galaxies with unprecedented clarity. Its measurements should resolve the tension by providing a third independent check. Instead, they've confirmed the tension exists. Meanwhile, the Atacama Cosmology Telescope collaboration published refined measurements in 2024 showing 67.9 kilometers per second per megaparsec, closer to Planck's value. The South Pole Telescope, another CMB experiment, reported 67.5 in their 2025 analysis. The early universe measurements are clustering around 67 to 68. The late universe measurements are clustering around 72 to 74. The gap is real, persistent, and growing more statistically significant with better data. What could explain this? Let's examine the possibilities with the same skeptical rigor we've applied to consciousness speculations. First possibility, systematic error. Maybe one or both methods have subtle, systematic biases that haven't been identified. But both approaches have been scrutinized exhaustively by independent teams. The systematic errors would have to be extremely clever to evade detection after 2 decades of intensive study. Possible, but increasingly unlikely. Second possibility, new physics in the late universe. Maybe dark energy has evolved over cosmic time, becoming stronger recently. This would mean the expansion rate genuinely is higher now than standard models predict based on early universe observations. Dr. Vivian Poulin from the University of Montpellier has developed, quote, 36 models where a component of dark energy existed in the early universe but has since decayed away. In a 2024 paper, her team showed these models could potentially explain the Hubble tension while remaining consistent with other observations. But they require adding new parameters to cosmology, and physicists are reluctant to add parameters without independent evidence. Third possibility: new physics in the early universe. Maybe something about the cosmic microwave background that we don't understand is affecting Planck's measurements. Perhaps there are extra relativistic particles, unknown neutrino species, or other exotic particles that were present in the early universe and affected the CMB in ways our models don't capture. Dr. Cora Dvorkin from Harvard University has explored this possibility, showing in a 2023 paper that extra dark radiation in the early universe could potentially ease the tension. But again, there's no independent evidence for such particles. Fourth possibility: we live in a cosmic void. Maybe our local region of space has lower than average density, creating unusual expansion dynamics. In such a scenario, local measurements would naturally give different results than global averages inferred from the CMB. Dr. Benjamin Bowes from the University of Edinburgh calculated in a 2024 paper that we'd need to live in a void roughly 2 billion light-years across, much larger than any observed void, to explain the full Hubble tension. Galaxy surveys show some evidence for local underdensity, but nothing approaching the required scale. Fifth possibility: something fundamental about general relativity or cosmology is wrong. Maybe gravity doesn't work the way we think on cosmological scales. Maybe the universe isn't as homogeneous as we assume. Maybe the Friedmann equations that describe cosmic expansion need modification. This is the most radical possibility, and the one most physicists resist, because general relativity has passed every other test with flying colors. But if all conventional explanations fail, we might have to consider unconventional alternatives. The situation is reminiscent of a crisis in physics from the 1920s, when spectroscopic measurements showed that different elements emitted light at precise, discrete frequencies. Classical physics couldn't explain it. The atoms should emit a continuous spectrum, not discrete lines. Physicists tried increasingly elaborate modifications to classical theory, adding epicycles to epicycles, but nothing worked. The resolution came from abandoning classical physics entirely and accepting quantum mechanics, a framework so counterintuitive that even its founders struggled to believe it. Are we facing a similar crisis now? Is the Hubble tension telling us that cosmology needs a quantum mechanics scale revolution? Dr. David Spergel, president of the Simons Foundation and a leading cosmologist, said in a 2024 lecture that the tension _quote _37 because resolving it could require fundamentally new physics that would reshape our understanding of the universe. But let's step back from the crisis and examine what's happening with gravitational wave detection, because this is where the most exciting developments are occurring. The pulsar timing arrays have now accumulated over 20 years of data on dozens of pulsars. The gravitational wave background signal they detect is not just a simple hum. It has structure, frequencies, patterns that reveal information about the sources. Dr. Sarah Vigeland from the University of Wisconsin-Milwaukee led an analysis published in 2025 that, for the first time, resolved individual supermassive black hole binaries contributing to the background. The technique is called, quote, 38 detection, and it works like picking out individual voices in a crowded room once you've learned to filter the background noise. By analyzing correlations between pulsar timing residuals at specific frequencies, Vigeland's team identified gravitational wave signatures from approximately 15 individual black hole binaries in nearby galaxies. The most prominent is in the galaxy NGC 4472, about 55 million light-years away, where two black holes, each containing about 1 billion solar masses, orbit each other every 8 years. This is extraordinary because it means we're now doing astronomy with gravitational waves in the nanohertz frequency band. We're not just detecting the background anymore, we're resolving sources, measuring their properties, learning about supermassive black hole populations throughout the local universe.
And here's where it connects back to the Hubble tension. By measuring the redshift of the host galaxies and the gravitational wave frequency of their black hole binaries, we can independently determine cosmic distances and expansion rates. Dr. Chiara Mingarelli, whose work Writer Number 1 introduced, published a 2025 paper showing that with 50 loud sirens detected across different redshifts, pulsar timing arrays could measure the Hubble constant to within 3% accuracy, competitive with conventional methods, but completely independent. It would take another decade of observation to accumulate enough loud sirens. But by the mid-2030s, gravitational waves might resolve the Hubble tension by providing a third independent measurement that definitively favors one value over the other. Or, and this is the unsettling possibility, the gravitational wave measurement might give yet a third value, confirming that something fundamental about our cosmological models is broken. What if early universe methods give 67, late universe methods give 73, and gravitational waves give 70? That would indicate the expansion rate genuinely varies in ways our theories don't predict, possibly due to observer effects or quantum fluctuations or something we haven't imagined. The LISA mission, scheduled for launch in 2037, will probe gravitational waves at higher frequencies than pulsar timing arrays, but lower than LIGO. LISA will be exquisitely sensitive to waves from merging supermassive black holes at cosmological distances, billions of light-years away, looking back through billions of years of cosmic history. LISA will detect perhaps hundreds of these mergers, each one providing a standard siren measurement of cosmic expansion at a different epoch. By mapping expansion history from the present back to when the universe was less than half its current age, LISA will test whether dark energy has evolved over time. Dr. Neil Cornish from Montana State University, part of the LISA science team, has calculated the mission's capabilities. In a 2024 paper, he showed that LISA could detect changes in dark energy's equation of state parameter, W, of just 5% over cosmic time. If dark energy is dynamical rather than constant, LISA will reveal it. If the equation of state is exactly -1, as the cosmological constant predicts, LISA will confirm it to unprecedented precision. Either way, we'll know whether the universe is heading toward a big freeze or something more exotic. But there's another possibility that's even more intriguing. LISA might detect primordial gravitational waves from cosmic inflation. These waves, if they exist, would be the holy grail of cosmology, direct evidence of the universe's first fraction of a second, when quantum fluctuations were stretched to cosmic scales by exponentially rapid expansion. The signature would be subtle. Primordial waves contribute to the gravitational wave background at specific frequencies determined by the energy scale of inflation. LISA's sensitivity might just barely reach the threshold needed to detect them. If LISA does detect primordial gravitational waves, it would transform cosmology. We'd have direct information about physics at energy scales completely beyond the reach of particle accelerators. The Large Hadron Collider at CERN probes energies up to about 14 trillion electron volts, the highest energies accessible with human technology. Cosmic inflation occurred at energies perhaps 1 trillion times higher, in a regime where quantum gravity effects become important. Detecting gravitational waves from that epoch would be like having a particle accelerator the size of the universe. And here's where quantum spacetime becomes experimentally testable. Primordial gravitational waves should carry imprints of quantum gravity. The tiny quantum fluctuations that seeded cosmic structure weren't perfectly smooth. Quantum gravity introduces non-Gaussianity, deviations from simple, random noise patterns. These deviations would show up in the primordial gravitational wave spectrum as correlations between different frequencies, patterns that reveal information about Planck scale physics, the realm where space and time themselves become quantum mechanical. Dr. Alessandra Buonanno from the Max Planck Institute for Gravitational Physics has pioneered theoretical work on quantum gravity signatures in gravitational waves.
Her 2023 paper showed that advanced data analysis techniques applied to LISA observations could potentially detect quantum corrections to general relativity if they're present at the level predicted by some quantum gravity theories.
We're talking about effects at the Planck length, 10 to the minus 35 meters, the smallest meaningful distance in physics.
Yet these microscopic quantum fluctuations, amplified by cosmic inflation and evolution, might leave detectable traces in macroscopic gravitational wave signals. Think about what this means. We might be able to experimentally test quantum gravity, one of the deepest unsolved problems in physics, not by building tiny particle accelerators or collapsing matter into black holes, but by listening to the universe's heartbeat with extraordinary precision. The cosmic pulse encodes information about reality at every scale, from the Planck length to the cosmic horizon, from the first instant after the Big Bang to the present moment.
And we're developing the technology to decode that information. But here's where we must inject a heavy dose of realism. We might also be approaching the limits of what's knowable. The cosmic horizon limits how far we can see, currently about 46 billion light-years in any direction. Events beyond the horizon are causally disconnected from us. No signal from them can ever reach us. As the universe's expansion accelerates, the horizon shrinks in co-moving coordinates. Fewer and fewer galaxies remain observable. We're living in what might be the brief golden age of cosmology, when we can still observe enough of the universe to understand its large-scale properties. Dr. Abraham Loeb from Harvard University has written extensively about what he calls, quote, 39, the fate awaiting civilizations in the far future. In a 2020 paper, he calculated that within 2 trillion years, all evidence of the Big Bang will have disappeared. The cosmic microwave background will have been redshifted to undetectable wavelengths. Distant galaxies will have receded beyond the horizon. Future astronomers will observe a universe containing only their local galaxy group, surrounded by empty darkness, with no evidence of cosmic expansion or cosmic history. They might conclude they live in a static, eternal universe, never knowing about the Big Bang or the billions of galaxies that once were visible. But we face a subtler version of this problem right now. Quantum uncertainty and Planck scale effects create a fundamental noise floor below which we cannot probe. The Heisenberg uncertainty principle, a cornerstone of quantum mechanics, states that you cannot simultaneously know a particle's position and momentum with arbitrary precision. Applied to spacetime itself, this means you cannot measure distances below the Planck length or time intervals below the Planck time. These aren't technical limitations we might overcome with better instruments. They're fundamental features of reality, according to quantum theory. Dr. Jacob Bekenstein, the physicist who discovered black hole entropy, showed in a series of papers from the 1970s through 2000s that there's a maximum amount of information that can be contained in any region of space. This quote, 40, means the universe cannot have infinite information content. There's a maximum number of distinguishable states. Applied to cosmology, this implies there's a maximum precision with which we can measure cosmic parameters. We might be able to determine the Hubble constant to 5 significant figures, maybe 10, but not arbitrarily many. Eventually, quantum noise dominates. Are we approaching that limit? The Hubble tension represents a 9% discrepancy between measurements. Current observations measure the expansion rate to about 1% precision. Future experiments might reach 0.1%. But if quantum fluctuations of spacetime create fundamental noise at, say, 0.01%, then no future measurement will ever be more precise than that. The Hubble tension might be telling us we've reached the threshold where quantum cosmic properties become relevant. Dr. Giovanni Amelino Camiglia, whose work Writer Number 3 introduced, has developed specific predictions for quantum gravity phenomenology. His calculations suggest that the accumulation of quantum space-time fluctuations over cosmological distances should create dispersion in gravitational wave signals, high-frequency waves traveling at slightly different speeds than low-frequency waves. This effect would be incredibly tiny,
but LISA might be sensitive enough to detect it. If LISA observes gravitational waves from sources at different redshifts and finds dispersion consistent with quantum gravity predictions, it would be revolutionary. But if no dispersion is found, it would constrain quantum gravity theories, potentially ruling out entire classes of models. The remarkable thing is that we're living at the moment when these questions transition from philosophical speculation to experimental science. For the first time in human history, we have the technology to test whether space-time is fundamentally quantum mechanical, whether observer effects matter on cosmic scales, whether the universe has a maximum information content, whether consciousness and cosmology are fundamentally connected. These questions have been debated by philosophers for millennia. Now physicists can actually address them with data. But, and I want to be absolutely clear about this, we don't know the answers yet. The gravitational wave background has been detected, but we haven't yet resolved enough individual sources to do precision cosmology. LISA hasn't launched. The square-kilometer array is still under construction. The Hubble tension hasn't been resolved. The nature of dark energy remains mysterious. Quantum gravity is still theoretical. Everything I've described about quantum observer effects and cosmic consciousness and fundamental limits on knowledge might turn out to be wrong, rendered moot by some brilliant insight that resolves all these puzzles within conventional physics. That uncertainty is frustrating, but it's also thrilling. We're living at a pivot point in cosmic history and in humanity's understanding of reality. The questions we're asking are profound. What is the universe? What is space-time? What is consciousness? How are they related? Do observers shape reality or just perceive it? Is there a maximum knowable, or can knowledge grow without limit? These aren't just academic puzzles. They touch on the deepest questions about existence, meaning, purpose, and our place in the cosmos. Your heartbeat continues its steady rhythm, 72 pulses per minute, as it has for every moment of your life. You rarely notice it unless you consciously attend to it. The universe's heartbeat continues its accelerating rhythm, pulsing through gravitational waves that wash over you constantly, at frequencies taking years to complete one cycle. You've never noticed it because the wavelengths are so vast and the effects so subtle. But now you know it's there, and in knowing, you're participating in one of humanity's grandest projects. The project of understanding where we are, how we got here, what we're made of, and what it all means. The next decade will be crucial. The square-kilometer array will begin full operations, dramatically increasing the sensitivity of pulsar timing arrays. The James Webb Space Telescope will continue refining distance measurements to ever more distant galaxies. New CMB experiments will search for primordial gravitational waves with unprecedented sensitivity. Computer simulations will model cosmic structure formation with ever greater fidelity, testing whether our theories match observations. And theorists will continue developing frameworks to make sense of it all. Frameworks that might radically revise our understanding of space, time, matter, energy, and consciousness. By the late 2030s, when LISA begins operations, we'll know whether the Hubble tension has been resolved or deepened. We'll know whether dark energy evolves or remains constant. We'll have maps of the gravitational wave background spanning multiple frequency decades, revealing cosmic history from the present back to perhaps the first second after the Big Bang. We'll know whether quantum gravity effects are detectable or whether they remain below the threshold of observability. We'll be much closer to answering whether the universe is fundamentally classical or quantum, whether observers play a special role or are just complex physical systems like any other. But here's what we need to understand. Even if we answer all these questions, even if we measure the Hubble constant to arbitrary precision, even if we detect primordial gravitational waves and quantum gravity signatures, even if we map the entire history of cosmic expansion and structure formation, we still won't know everything. There will always be deeper questions. Science doesn't provide final answers. It provides progressively better approximations, more precise measurements, more comprehensive theories. Each answer opens new questions. Each mystery solved reveals deeper mysteries. The universe's heartbeat is accelerating. That much is certain. Whether it's accelerating toward heat death or towards something we can't yet imagine, whether consciousness plays a fundamental role or emerges incidentally from physical complexity, whether quantum effects matter on cosmic scales or remain confined to microscopic realms, whether observers shape reality or just perceive it. These remain open questions. But they're questions we're finally equipped to address with rigorous science, not just philosophical speculation. And that brings us to the most fundamental question of all, the one that underlies every measurement we make and every theory we construct. What can we know, and what are the limits of knowledge?
When we detect the cosmic heartbeat with pulsar timing arrays, when we measure its acceleration with space-based telescopes, when we map its quantum fluctuations with future gravitational wave observatories, are we discovering objective truths about an observer-independent reality? Or are we constructing frameworks that organize our experiences? Frameworks that might be fundamentally observer-dependent. This isn't just academic philosophizing. It matters for how we interpret the Hubble tension, for how we think about dark energy, for how we understand the relationship between quantum mechanics and cosmology. If there's an objective fact about the expansion rate, a single true value we're trying to measure, then the Hubble tension represents a measurement problem we must solve. But if the expansion rate is fundamentally observer-dependent, if different measurement methods probe genuinely different aspects of a quantum superposition, then the tension might be telling us something profound about the nature of reality itself. Dr. Carlo Rovelli, whose work on relational quantum mechanics writer number 3 introduced, argues that we need to abandon the idea of observer-independent facts entirely. In his view, physics should only describe relationships between systems, not absolute properties of an observer-independent world. Applied to cosmology, this would mean the Hubble constant doesn't have a single objective value. It has different values relative to different reference frames, different measurement schemes, different observational contexts. The universe's heartbeat would be like a jazz performance. The rhythm exists in the relationships between musicians and listeners, not as an abstract entity independent of performance and perception. This is radical, uncomfortable, and contradicts our intuitive sense that reality is _quote _ 41 _ independent of our observations. But it might be true. Quantum mechanics has forced us to abandon intuitions before. The idea that particles have definite positions before measurement. The idea that causation flows strictly from past to future. The idea that information cannot be destroyed. Perhaps cosmology will force us to abandon the intuition of observer independence as well. But there's another interpretation, equally valid mathematically, but completely different philosophically. The Everettian or many worlds interpretation that writer number 3 discussed. In this view, there is an objective quantum state of the universe, a wave function that evolves deterministically according to Schrödinger's equation. The appearance of measurement collapse, of quantum superpositions resolving into single outcomes, is an illusion created by decoherence. In reality, all possible outcomes occur in different branches of the universal wave function. The Hubble tension might reflect the fact that we're in a branch where early universe observations selected one expansion rate and late universe observations selected a slightly different rate, both coexisting in superposition at the quantum level, but separated into different branches of reality by the measurement process. In this interpretation, there are versions of you reading these words in universes with every possible Hubble constant value within the quantum uncertainty range. The cosmic heartbeat has every possible rhythm across the multiverse of quantum branches. You happen to experience one particular rhythm, not because it's objectively real in some special way, but simply because this is the branch of reality you happen to inhabit. Other versions of you experience different rhythms with equal validity. Which interpretation is correct? Relational quantum mechanics or many worlds? Observer dependence or observer multiplication? Frankly, current physics cannot answer this question. Both interpretations make identical predictions for any possible experiment. The choice between them is philosophical, perhaps even aesthetic. Some physicists find relational quantum mechanics more parsimonious.
Why postulate countless unobservable branches when a simpler observer-relative description suffices? Others find many worlds more parsimonious. Why postulate special laws for measurement collapse when deterministic wave function evolution explains everything? The cosmic heartbeat measurement cannot definitively resolve this debate because both interpretations accommodate it equally well. But what the measurement can do, what gravitational wave astronomy, precision cosmology, and quantum gravity experiments might achieve in coming decades, is constrain the space of possible interpretations. If we discover that quantum effects genuinely matter on cosmic scales, if we detect observer-dependent variations in supposedly objective cosmological parameters, if we find evidence that information is fundamentally relational rather than absolute, then interpretations emphasizing observer dependence become more attractive. If instead we find that quantum effects remain confined to microscopic scales, even in the most sensitive cosmological measurements, then more objective interpretations retain their appeal. What we're witnessing, in other words, is science approaching its epistemological boundaries, the limits not of what we can measure, but of what measurement means. The cosmic heartbeat, pulsing through gravitational waves at frequencies taking years to cycle, carrying information about reality from the Planck scale to the cosmic horizon, from the Big Bang to the far future, is simultaneously our best tool for probing these boundaries, and a phenomenon whose very existence raises questions about whether the boundaries can be transcended. Your heartbeat, pulsing 72 times per minute in your chest right now, is entangled with the cosmic heartbeat through chains of causation extending back to the Big Bang. The atoms in your body were forged in stars that formed when gravity overcome cosmic expansion, pulling matter together in regions where quantum fluctuations created slight overdensities in the primordial universe. Those stars eventually exploded, scattering heavy elements into space, where they eventually coalesced into the solar system, the Earth, and eventually you. The rhythm of your heart depends on biochemistry, that depends on chemistry, that depends on atomic physics, that depends on nuclear physics, that depends on cosmological history, that depends on the universe's expansion rate. If the Hubble constant were significantly different, if cosmic expansion were much faster or much slower, the chain of causation leading to your existence would be broken. Stars might not form the right elements. Galaxies might fly apart before solar systems could evolve. Life might never emerge. The fact that you exist to measure the cosmic heartbeat constrains what values that heartbeat can have through the anthropic principle writer number 3 explored. But now we see the constraint runs both ways. The cosmic heartbeat constrains you just as your existence constrains it. Observer and observed, measured and measurer, consciousness and cosmos. These aren't separate entities interacting across a gap. They're aspects of a unified system, co-determining each other in a loop of circular causation that defies conventional understanding. This is where science reaches its limit and philosophy begins. Or perhaps, this is where we realize science and philosophy were never truly separate, just different angles on the same fundamental project. Understanding what it means to exist, to experience, to know. The cosmic heartbeat measurement, pulsar timing arrays detecting gravitational waves, space telescopes measuring cosmic expansion, quantum gravity experiments probing Planck-scale physics, is simultaneously an empirical scientific program and an existential philosophical inquiry. We're not just measuring the universe, we're asking what it means to measure, what it means to know, what it means to be a conscious observer embedded in a quantum cosmos. The answers we discover in coming decades will reshape civilization. If we confirm that quantum effects matter on cosmic scales, it will transform technology as profoundly as the original quantum revolution transformed the 20th century. If we detect primordial gravitational waves and decode their quantum signatures, we'll unlock information about physics in regimes completely beyond the reach of Earth-based experiments. If we resolve the Hubble tension and determine the universe's ultimate fate, we'll know whether our species has trillions of years ahead or whether cosmic acceleration will eventually render the universe uninhabitable. But beyond practical implications,
beyond technological applications, beyond even the question of cosmic fate. What matters most is this. We're discovering what kind of universe we inhabit. Is it a clockwork mechanism, deterministic and observer-independent, where consciousness is an incidental byproduct of complex chemistry? Or is it a participatory universe, quantum-entangled and observer-dependent, where consciousness plays a fundamental role? Is there a maximum knowable, or is knowledge potentially unbounded? Are we discovering truth or constructing frameworks? Are we measuring reality or creating it through the act of measurement? The universe's heartbeat, accelerating, pulsing, resonating through space-time, doesn't answer these questions, but it focuses them with unprecedented clarity. In the rhythm of gravitational waves, in the tension between measurements, in the quantum fluctuations underlying everything, we see our own deepest questions reflected back at us. The cosmos is a mirror, and what we discover when we measure its heartbeat is as much about ourselves as about the universe. But perhaps the deepest insight isn't about what we've measured or what we might discover. Perhaps it's about what measurement itself reveals, not just about the universe, but about the relationship between consciousness and cosmos, between the act of observation and the nature of reality. When you measure your pulse, you're detecting rhythmic contractions of cardiac muscle, driven by electrochemical signals. Simple cause and effect, predictable and mechanical. But when you measure the universe's pulse, when pulsar timing arrays detect gravitational waves, when telescopes capture light from distant galaxies, when experiments probe the cosmic microwave background, you're not just detecting something external. You're participating in a relationship between observer and observed that might be more fundamental than either one separately. Dr. John Archibald Wheeler, the physicist who coined the term black hole and spent his final decades contemplating the role of observation in physics, proposed what he called the participatory universe. In a 1978 paper, he argued that observers aren't simply passive recorders of pre-existing reality, but active participants in bringing the universe into being through acts of measurement. He illustrated this with a diagram showing a giant U, the universe, with a giant eye emerging from one arm of the U, looking back at itself. The eye represents consciousness arising from matter, then turning back to observe the matter from which it emerged. Observer and observed form a self-referential loop. Wheeler's vision sounds mystical, but it emerges from taking quantum mechanics seriously. Quantum mechanics tells us that systems exist in superposition, multiple states simultaneously, until measured. Measurement collapses the superposition into one outcome. But if the universe itself is a quantum system, as all evidence suggests, then what collapses its wave function? Wheeler's answer? Observers within the universe collapse the wave function through their observations. But those observers only exist because earlier quantum collapses created the conditions for life. Past and present, observer and observed, measurement and reality are caught in what Wheeler called a, quote, 44 of mutual causation extending across cosmic time. The cosmic heartbeat fits into this framework beautifully and terrifyingly. When pulsar timing arrays detect gravitational waves from billions of years ago, they're not just recording ancient history. In the quantum view, those waves existed in superposition, a quantum haze of possible amplitudes, phases, and frequencies until detected. The detection collapses the superposition retroactively, determining which version of cosmic history actually occurred. Your existence as a conscious observer capable of detecting the cosmic pulse depends on cosmic history having unfolded in a way that allows life. But cosmic history's unfolding might depend, in some quantum sense, on being observed by conscious beings like you. Now take this thought to its extreme and ask, what does it mean that the cosmic heartbeat is accelerating? In the straightforward interpretation, it means dark energy is driving ever faster expansion, pushing the universe toward eventual heat death. But in Wheeler's participatory framework, acceleration might be revealing something about the relationship between consciousness and cosmos. The universe has been expanding for 13.8 billion years,
but conscious observers capable of measuring that expansion have existed for only an infinitesimal fraction of that time, perhaps a few thousand years at most, if we count only civilizations with scientific instruments.
What happens to the cosmic heartbeat during the trillions of years when no observers exist to measure it? In the many worlds interpretation, it exists in superposition across all possible branches. In the relational interpretation, it has no definite value. It's only defined in relationship to measurement. In Wheeler's participatory view, it's literally brought into definite existence by the act of observation. The universe might be like Schrödinger's cat writ large, simultaneously in multiple states until consciousness observes it and collapses the superposition. But here, we must be exquisitely careful not to slide into mysticism or wishful thinking. The role of observation in quantum mechanics is not about consciousness being magical or about thoughts creating reality in the way pseudoscience claims. It's about information theory and thermodynamics, about the physical process of a system becoming entangled with its environment in irreversible ways. When we say measurement collapses the wave function, we don't necessarily mean a conscious mind performs magic. We mean that quantum information becomes encoded in the environment in a way that makes one outcome definite and others inaccessible. Dr. Wojciech Zurek's quantum Darwinism, which writer number 3 introduced, makes this precise. Certain quantum states are more stable, more easily copied into the environment through interactions. These _46_ become classical facts that multiple observers can agree on. The cosmic heartbeat's rhythm, the specific pattern of gravitational waves we detect, might be a pointer state that emerged through quantum Darwinism, naturally selected from the space of possibilities, not by consciousness per se, but by the physical process of quantum information propagating and being recorded in the environment. So where does this leave consciousness? Perhaps consciousness is not fundamentally different from other physical processes. It's just a particularly complex form of information processing that happens to be capable of reflection and self-awareness. When you become aware of your heartbeat, neurons in your brain are processing information about cardiac signals. When you become aware of the cosmic heartbeat through scientific measurement, neurons are processing information about space-time distortions. Both are physical processes involving information transfer, but one of them, human consciousness, has the remarkable property of being able to contemplate itself, to ask questions about its own nature, to wonder about its relationship to the cosmos. This brings us to the fundamental mystery that underlies everything we've discussed. What is consciousness actually? We know it emerges somehow from the brain, from electrochemical signals passing between roughly 86 billion neurons, each connected to thousands of others in an incomprehensibly complex network. We know it correlates with certain patterns of neural activity, specific oscillations, synchronizations, information flows that neuroscientists can measure. But we don't know how or why these physical processes give rise to subjective experience, to the feeling of what it's like to be you, to the direct qualitative sensation of hearing music or seeing red or feeling your heartbeat. Dr. David Chalmers, a philosopher at New York University, calls this the hard problem of consciousness. The easy problems, and they're not actually easy, just easier, involve explaining the brain's information processing capabilities, attention, memory, learning. These are difficult but tractable scientific questions. The hard problem is explaining why there's something it's like to be conscious, why physical processes in the brain are accompanied by subjective experience. No current theory of consciousness fully solves this problem. We have frameworks, models, hypotheses, but no consensus on how matter gives rise to mind. And this connects directly to the cosmic heartbeat, because measurement ultimately requires consciousness somewhere in the chain. A pulsar timing array consists of radio telescopes, atomic clocks, computers running analysis algorithms, all unconscious physical systems exchanging information. But at some point, a human scientist looks at the results, interprets the data, draws conclusions. That scientist's consciousness is what makes the measurement meaningful, what transforms raw information into knowledge.
Without consciousness somewhere in the process, there are just physical systems exchanging signals, quantum states becoming entangled, information being recorded, but no one for whom that information means anything. Perhaps, and this is speculation, not established science, consciousness and the cosmic heartbeat are related because both are fundamentally about time. Your subjective experience has a flow, a direction, a sense of past, present, and future. The cosmic heartbeat has cycles, oscillations, rhythms that define temporal structure on cosmic scales. Your heart beats roughly once per second, creating a natural unit of biological time. The gravitational wave background oscillates with periods of years to decades, creating a natural unit of cosmological time. Both are clocks. Both mark time's passage. Both create temporal structure in otherwise timeless physical laws. Modern physics treats time very differently than our everyday experience suggests. Einstein's relativity shows that time is relative. Different observers experience different rates of time flow depending on their motion and gravitational environment. Quantum mechanics treats time as an external parameter, not an observable property of quantum systems. Some interpretations of quantum gravity suggest time might not be fundamental at all, but emergent from something more basic, perhaps from quantum entanglement, as Dr. Carlo Rovelli proposes, or from the evolution of cosmic entropy, as Dr. Sean Carroll suggests. But consciousness experiences time as flowing, as moving inexorably from past through present toward future. You remember the past, but not the future. You can influence the future, but not the past. This asymmetry, the arrow of time, is one of the deepest puzzles in physics, because the fundamental laws are time-symmetric. Newton's laws, Maxwell's equations, Einstein's relativity, even quantum mechanics at the fundamental level, all work equally well running forward or backward in time. The arrow of time emerges from thermodynamics, from the statistical tendency of systems to evolve from low entropy to high entropy. But why was the early universe in a low entropy state to begin with? Nobody knows. The cosmic heartbeat connects to this because the universe's expansion creates the arrow of time on cosmic scales. As space expands, the density of matter and radiation decreases. This expansion is irreversible. You can't spontaneously contract an expanding universe. The expansion creates a temporal orientation. There's a past with higher density and a future with lower density. Your consciousness experiences time as flowing in the same direction as cosmic expansion, from past to future, from Big Bang toward whatever ultimate fate awaits. This might not be coincidence. Perhaps consciousness can only exist in systems where entropy is increasing, where there's a thermodynamic arrow of time pointing from past to future. Perhaps the cosmic heartbeat and your subjective experience of time flow are different manifestations of the same underlying phenomenon, the universe's irreversible evolution from low to high entropy. But now, and this is crucial, we must confront what we don't know. For all the extraordinary progress in cosmology, gravitational wave astronomy, quantum mechanics, and consciousness studies, the deepest questions remain unanswered. We don't know what dark energy is. We've named it, measured its effects, tracked its influence on cosmic expansion over billions of years, but we have no idea what it actually is. It might be vacuum energy, a cosmological constant, a property of empty space itself. Or it might be a new field, a dynamic component of the universe that evolves over time. Or it might be something we haven't imagined yet, something that will require fundamentally new physics to understand. We don't know what dark matter is either, the invisible substance that makes up about 27% of the universe's total mass energy content. We know it must exist because galaxies rotate too fast to be held together by visible matter alone. We know it must be gravitationally clumping on large scales because its gravitational lensing effect bends light from distant galaxies. But despite decades of searching with increasingly sensitive experiments, we haven't directly detected a single dark matter particle. It might be composed of weakly interacting massive particles, or axions, or primordial black holes, or something entirely unexpected. We don't know how to reconcile quantum mechanics and general relativity. Both theories are extraordinarily successful within their domains. Quantum mechanics for the microscopic world of atoms and particles, general relativity for the macroscopic world of stars and galaxies. But they're mathematically incompatible. When you try to apply quantum mechanics to gravity, you get nonsensical infinities. When you try to apply general relativity to quantum systems, you lose the uncertainty principle. String theory, loop quantum gravity, and other approaches attempt to bridge this gap. But none has made testable predictions that would allow us to confirm or refute them.
We don't know whether the universe is finite or infinite in spatial extent. Observations show the universe is very large, at least 93 billion light-years in diameter, possibly much larger or even infinite. We don't know if there are other universes beyond our own. The multiverse remains speculative, despite appearing naturally in many theoretical frameworks. We don't know why the laws of physics are what they are, why the fundamental constants have the values they do, why the universe exists at all rather than nothing. We don't know what happens inside black holes, beyond the event horizon where our observations cannot reach. We don't know if information is preserved when black holes evaporate through Hawking radiation, or if it's destroyed, creating a paradox that would require revising quantum mechanics. We don't know if time had a beginning at the Big Bang, or if something existed before.
We don't know what will happen in the universe's far future, whether it will expand forever, recollapse, tear itself apart in a big rip, or experience some other fate we haven't predicted. And most fundamentally, we don't know the relationship between consciousness and physical reality. We don't know if consciousness is purely a product of complex information processing that could in principle be replicated in artificial systems, or if it requires something beyond computation, quantum effects in neurons perhaps, or something even stranger. We don't know if consciousness plays a fundamental role in quantum mechanics, actively collapsing wave functions, or if it's just another physical system obeying the same laws as everything else.
We don't know if other animals are conscious, or artificial intelligences might become conscious, or even whether we can definitively prove that other humans are conscious beyond our own subjective certainty of our own consciousness. These are not temporary gaps in knowledge that will be filled by a few more decades of research. They're fundamental mysteries at the boundaries of what might be knowable. Some of them might have answers we'll discover. Dark matter could be detected tomorrow if we build the right detector in the right place. Others might be permanently beyond the reach of observation. We can never see what lies beyond our cosmic horizon, and we can never directly experience another person's subjective consciousness. And some questions might not even have definite answers. If quantum mechanics is fundamentally probabilistic rather than deterministic, then the universe's future isn't uniquely determined, and asking what will happen is asking the wrong question. The cosmic heartbeat measurement reveals this uncertainty rather than resolving it.
Yes, we've detected gravitational waves. Yes, we've measured cosmic acceleration. Yes, we've mapped the universe's large-scale structure with extraordinary precision. But every answer raises new questions. Why does dark energy have exactly the strength it does? Why did the universe's expansion begin accelerating 6 billion years ago rather than earlier or later? What determines the gravitational wave background spectrum? Do quantum effects matter on cosmic scales or remain confined to the microscopic? Is there a maximum precision with which we can measure cosmological parameters, or can measurements become arbitrarily precise? The Hubble tension, that persistent 9% discrepancy between different measurements of cosmic expansion, might be a hint that we're approaching the limit of what's knowable with our current theoretical framework.
Or it might be a technical problem that will be resolved by better observations.
Or it might be revealing genuinely new physics that will require revising cosmology as fundamentally as quantum mechanics revised classical physics. We don't know. And the honest acknowledgement of uncertainty is essential to good science. Certainty belongs to ideologies, not to empirical investigation of reality. Dr. Richard Feynman, one of the greatest physicists of the 20th century, said in a 1963 lecture, quote, This intellectual humility, this willingness to say, quote, 50, is what distinguishes science from dogma. The cosmic heartbeat measurement doesn't give us absolute truth about the universe. It gives us better approximations, more precise measurements, deeper questions.
And that's exactly what science is supposed to do. So where does this leave us? Here, now, in this moment, as you read these words and feel your heart beating in your chest. Let's return to where we began, to the parallel between your pulse and the cosmos's pulse, but now with the accumulated weight of everything we've explored. Your heart is beating, 72 times per minute, approximately 1.2 times per second, about 100,000 times per day. This rhythm has continued uninterrupted since before you were born, since your heart first formed as a cluster of cells in your mother's womb about 3 weeks after conception. It will continue until the moment of your death, which might be decades from now, or might be today. There's no way to know for certain. The universe's heartbeat is pulsing through gravitational waves, oscillations with periods of years to decades, wavelengths of light years, amplitudes measured in billionths of a meter. This rhythm has continued for billions of years, shaped by the orbital dance of supermassive black holes, by the quantum fluctuations in the early universe, by the mysterious influence of dark energy. It will continue for trillions of years into the future, long after your heart has stopped, long after the Earth has been consumed by the dying sun, long after the last stars have burned out and the universe has gone cold and dark. Both rhythms, your biological pulse and the cosmic pulse, are temporary phenomena, brief flickers of organized complexity in a universe trending inexorably toward maximum entropy. Your heartbeat depends on carefully maintained disequilibrium, oxygen gradients across cell membranes, electrical potential differences between neurons, thermal gradients between your body and the environment. When equilibrium is reached, when oxygen is evenly distributed, when electrical potentials balance, when temperatures equalize, your heart stops beating and you die. The cosmic heartbeat depends on gravitational disequilibrium, massive objects in orbit around each other, structures in the universe not yet dispersed by expansion, energy gradients that allow for change and evolution. When cosmic equilibrium is reached, when all massive objects have merged or dispersed, when expansion has isolated every galaxy, when all energy gradients have been exhausted, the cosmic heartbeat stops and the universe reaches heat death. But right now, in this brief cosmic moment between the Big Bang and the heat death, both heartbeats are going strong. Your heart is beating. The universe's heart is beating. And somehow, miraculously, you are conscious of both. You can feel the pulse in your wrist or neck. You can contemplate the gravitational waves passing through your body at this very moment, stretching and compressing space-time by amounts far smaller than an atomic nucleus, but nonetheless real, measurable, present. You can hold both rhythms in your mind simultaneously, the biological and the cosmological, the intimate and the infinite, the personal and the universal. This is what it means to be a conscious observer in a quantum cosmos, to be simultaneously part of the universe and capable of contemplating the whole universe. To be made of atoms forged in stars, while also being able to study those stars and understand their life cycles. To be subject to the laws of physics, while also being able to discover what those laws are. To be mortal, temporary, a brief pattern of organized complexity, destined to dissolve back into randomness, while also being able to ask questions about mortality, temporality, and the meaning of existence. The parallel between your heartbeat and the cosmic heartbeat isn't just a poetic metaphor. It's a genuine, physical connection. The calcium ions flowing through your cardiac cells obey the same electromagnetic laws that govern the motion of charged particles in distant galaxies. The space-time curvature created by your body's mass, infinitesimal though it is, contributes to the total curvature of the universe. The quantum particles in your brain are entangled with quantum particles throughout the cosmos, through chains of interaction extending back to the Big Bang. You are not separate from the universe, observing it from outside.
You are the universe observing itself, a localized region of space-time where complexity has reached sufficient density to generate consciousness and self-awareness. And perhaps, though this remains speculative, consciousness is what gives the universe's heartbeat its full meaning. A gravitational wave passing through empty space is just a ripple in space-time, a mathematical solution to Einstein's field equations, a physical phenomenon with no intrinsic significance. But a gravitational wave detected by conscious observers, measured with pulsar timing arrays, analyzed with sophisticated algorithms, contemplated by minds capable of wonder and curiosity, that becomes something more. It becomes knowledge, understanding, a part of the ongoing project of consciousness trying to comprehend the cosmos from which it emerged. Dr. Freeman Dyson, in his final book published shortly before his death, wrote, quote, "He wasn't arguing for intelligent design or supernatural creation. He was noting the remarkable fact that the universe's physical parameters lie within the narrow range compatible with complexity, life, and consciousness. If the strong nuclear force were slightly weaker, no atoms heavier than hydrogen could form. If gravity were slightly stronger, stars would burn out too quickly for life to evolve. If dark energy were much larger, galaxies would never form. The universe is, in some deep sense, fine-tuned for observers. Perhaps the universe's heartbeat, its particular rhythm of expansion and oscillation, is part of that fine-tuning. Perhaps the specific strength of dark energy, the timing of its domination over matter and radiation, the rate at which the heartbeat is accelerating, are all constrained by the anthropic requirement that observers exist to measure them. Or perhaps it's even stranger. Perhaps the act of observation itself, distributed across all conscious beings throughout cosmic history, participates in determining what the heartbeat is through quantum wave function collapse, operating retroactively across billions of years. We don't know. And in some sense, that's the most important realization of all. The cosmic heartbeat is real. We've detected it, measured it, mapped it with increasing precision. But what it means, why it's accelerating, how it relates to consciousness, whether it will continue forever or eventually stop, these remain mysteries. Science has given us extraordinary tools for measuring reality, but measurement alone doesn't exhaust meaning. The universe's pulse beats on, carrying information we're only beginning to decode, raising questions we're only starting to formulate, revealing depths of mystery that might never be fully plumbed. Right now, as you finish reading these words, your heart is still beating. The universe's heart is still beating. Both will continue for a while. Your heart for decades, perhaps. The universe's heart for trillions of years. Eventually, both will stop. Both will return to equilibrium. Both will become part of the cosmic background. But in the meantime, in this brief interval between origin and end, something remarkable is happening. Consciousness has emerged from matter. Observers have arisen from the observed. Minds have developed the capacity to contemplate the cosmos and ask why anything exists at all. Perhaps that's enough. Perhaps the universe's heartbeat doesn't need a deeper explanation beyond the physics we're discovering. Dark energy, gravitational waves, quantum mechanics, general relativity. Or perhaps consciousness and cosmos are more deeply connected than our current science acknowledges, linked through quantum entanglement or information theory, or something we haven't imagined yet. Perhaps future observations will resolve the Hubble tension, detect primordial gravitational waves, measure quantum gravity signatures, and finally, answer the deepest questions about the universe's nature and fate. Or perhaps some mysteries will remain permanently beyond the reach of measurement, knowable only through lived experience, through the direct subjective awareness of being conscious in a cosmos that somehow gave rise to consciousness. The cosmic heartbeat continues. Your heartbeat continues. And between these two rhythms, one vast beyond comprehension, one intimately familiar, lies the entire mystery of existence. We measure, we theorize, we observe, we wonder. We detect gravitational waves with pulsar timing arrays spanning the galaxy. We map the cosmic microwave background to millionths of a degree precision. We calculate the universe's expansion rate to fractions of a percent accuracy. And yet the deepest questions remain. What is the universe? What is consciousness?
How are they related? Why does anything exist? What does it all mean?
Science cannot answer these questions completely because they transcend empirical measurement. But science can illuminate them, constrain them, transform vague wondering into precise investigation. The cosmic heartbeat is no longer a poetic metaphor. It's a measurable physical phenomenon with specific properties, testable predictions, falsifiable implications. And in measuring it, we're simultaneously measuring ourselves, our capabilities, our place in the cosmos, the relationship between observer and observed.
So let the heartbeat continue, yours and the universe's, biological and cosmological, personal and cosmic. Let it pulse through space-time, through neurons, through consciousness, carrying information from the depths of the quantum realm to the vastness of cosmic horizons. Let it remind you that you are both infinitesimally small, a brief pattern of atoms on a tiny planet orbiting an ordinary star in an ordinary galaxy among trillions, and cosmically significant. The universe's way of knowing itself, consciousness emerging from matter to contemplate matter, observers arising to measure the cosmic pulse. The universe has a heartbeat. You have a heartbeat. Both are mysteries. Both are facts. Both are miracles of organized complexity, temporarily defying entropy's universal tendency toward disorder. And both, yours and the cosmos's, the measured and the measurer, the observed and the observer, are inextricably linked through chains of causation, quantum entanglement, and perhaps something even deeper that we're only beginning to understand. The pulse continues, the mystery deepens, and consciousness observes it all, wondering.